Oh, so I don't forget. Haha, so I didn't forget. Got it.
Oh, yeah. It illuminated me.
Istituto 9 più 10 qui da parte mia, ma sono un po' altalenante. Da Trieste, Roberto, buona serata. Guardare valvole come si comportano, capito? Se mando su altro che fa subito in protezione, non sappiamo il motivo. The signal it is between 5.8 to 5.9, Roger? Please repeat the question. Yes, it's similar signal is quite the same.
Well, I'm here. People are getting here. If anybody has any questions they want to ask, now's a great time.
Can you change my name?
Uh,
I'm iPad.
yes. That Anna.
Yep.
Go.
Good morning.
Morning. That was the easiest request of the whole day, I bet.
Question,
Yep.
is the test open book?
No. Now, what fun would that be? Other questions?
How many minutes are you allowed to have for
Infinity. To take the test? Infinity. Yeah, I like to tell this story that I've been a volunteer examiner since 1987 when I was 18. And I mean, I've tested thousands and thousands of people during those years, all these years. And we had this one guy come in, and there were three people coming in to take tests on a Saturday morning at 8 o'clock. And this one guy came in, and he called and let me know he was going to be there, and he showed up, and he came in with no license, and like, all right, well, let's start with the code and everything. And so we started with 20 words a minute, and he aced that. And so he started with the written exams, like, oh, this will be a piece of cake, right? I don't know how far he's going to go, and he pulls out, and he's wearing his super thick glasses, and he pulls out his magnifier. And he starts with the first question. You know, you can see how fast he's going, and he's got this giant magnifier, and he's like face down in the test. And like 45 minutes later, he's done with the first test. I'm like, how far do you want to go today? It's like, well, I want to do them all. We started at 8 o'clock. By 2 in the afternoon, he had finished. So, usually, we would go in for an 8 o'clock morning exam and we'd be out of there by 10 o'clock. Right. And so there are 3 of us who are giving the exams. We're like, okay, well, who's going to go get lunch? We can't leave the room. Got to either wait till he's done with one or ask somebody outside to go get us some lunch or something. And we're trying to figure out what to do for 6 hours. So, but he made it all the way to extra in one sitting.
Scott, I have a question.
Okay.
So yesterday, is it JD that came on and?
Yeah.
Yeah. And he gave us the link. We went to it, and then I noted that it didn't have the exam today. It had other exam dates.
And then I actually put the updated
Yes.
one in there.
Yes. So that's for today. So are those the other offerings that were listed on the site he gave us, those are other dates that we can schedule and take the exam then?
Yep.
Okay.
I mean, we examine every single day except for Sunday, and today is special. So,
right. Okay.
So, if you are, just let me grab see what it looks like.
Could you send that link again or put it in the chat, please?
I was just going out to grab it.
Appreciate you.
Is that the
And
recording yesterday?
yeah, but here's the link for today. That's for the and when we go there, it looks like this. And notice you've got 20 of 26 slots claimed. So we have spots.
Right.
So there you go. And it's 8 o'clock. That means it's time for me to slam the door to the room so nobody interrupts me. And it's time to get started. All right. Anybody? Questions? Like I said, if you've got questions, other people do too. I'm sure.
The link for the recording yesterday, I'm a scout leader and I would love to share it with other scouts in my group who are interested in this. How would I find the link for
I sent it out to everybody via email last night.
Yeah.
I didn't get an email.
Did anyone else not get it?
I got it
Okay.
and replied.
Okay. Here's the, it was radio class first day video and tomorrow's events. So if you didn't get it and you want it, just send me a note, which is really strange because you obviously signed up via email and I've got a big list of it, but it doesn't mean that it was guaranteed to work. So
Okay.
just drop the email directly to me in the chat and I'll forward it to you. Make sure you get it.
Looks like 8:49 Pacific time.
I believe that. Okay.
Hey, Scott,
Yeah.
will you be offering this class again? I have a couple friends wanting to do it.
I usually do, but as you can imagine, it kind of takes a little
Life
bit out of
takes-
me.
Yeah.
And I do have a full-time job and I have a wife and 2 kids and lots of other things going on too. So I kind of squeeze it in when I can, I can only I suddenly see this time oh, I can do it. I can do this. And then I go ahead and schedule it. And I
Okay.
usually do it a month in advance, but here's the
Do you
thing.
send an email out?
If I've got your email address, I keep track of all those emails. I have a nice big email list. And so you might get some emails from me in the future saying, hey, there's a class coming up. Tell your friends.
Yeah. We would like
Okay.
to. Thank you.
Yeah, I'd definitely be able to send it out to some people too. So.
Well, and it's funny because like I said, I've done classes where I only had 5 or 6 people. And clearly this one is not like that. I only advertised this one time.
Yes.
I mean, it was a month ago and I advertised one time
Why don't you
So-
charge?
because I don't want to charge. This is my way of giving back. You know, so I don't want to charge. I know I could, but I mean, do you want to be charged?
I'm glad you didn't charge,
It would have been worth it.
but I
Yeah,
would have
but
paid it.
right.
paid
Well,
it.
Yeah, I'm glad you didn't charge.
yeah. And the thing is that now, you know, you can look at it and say, oh, you know, I got a class for free and I can pay that forward. So, you know, I mean, I could, but there are lots of other groups. Like I know there are some groups that charge $50, $60 for a class. And they're fine. I mean, that's not a lot for a 2-day class, but you know, I'd rather do it for free.
Maybe there's a way of donating.
You know, there's always a way of donating, but you know what I would say? Go join your local club, make the donation to the local club.
There you go.
You know,
find-
and
Go
go
find,
get
go,
somebody. Yeah.
go make a new ham radio operator somewhere once you know what you're doing.
Exactly.
You know, go make somebody new. You know, give them the skill that you're picking up. So, all right, everybody ready to do this?
Let's do it.
Okay, here we
Yeah.
go. It's Sunday.
go.
Okay, so this is the easy day. Yesterday was the hard day, and that's the other reason that I do 8 hours one day and 4 hours the next, because there's the hard day followed by the easy day. So one of the things that I'd like to bring up is this website called HintLink RF calculator. Okay. So this is actually what I was going to bring up yesterday, but I didn't get to. So everybody see that?
Yes.
Okay,
Yeah.
so I'm going to put it in chat. Here's the link to it. And what's cool about this is that notice that this references FCC OET 65,
Yes.
right? Instead of actually having to go and figure it out yourself, somebody actually did it.
Bless them.
Yes. So, you know, that's part of the paying it forward thing, right? So, okay, average power, that's average, it's time average. So if you're 100 watts and you're 20% of the time, you'd be 20 watts. Dipole, 2.2 dBi. So that's something that we haven't brought up yet. dBi versus dBd. Distance to the antenna, let's say you're 10 meters away and you're at 144 megahertz and go. So this says, okay, here's your estimated power density based on the information you gave them. Controlled environment in milliwatts per square centimeter and uncontrolled environment. Those are your limits. Obviously, you're way below that. Now, interestingly enough, the most dangerous thing you can do, let's say you have a handheld radio and you're running 5 watts half the time. You're having a conversation with somebody. Your antenna gain, we're going to say it's a dummy load rubber duck antenna, and interest to the from distance from the radio is about 0.2 meters, which is a handheld radio. And whoa, look at that. So controlled environment means you know what you're doing. Uncontrolled environment means somebody's just walking by. In the case of a handheld radio, well, you know, that would be a controlled environment because nobody's going to, you know, get into that area closer than you. But notice that a handheld radio running 5 watts half the time is actually no, it's not safe. So that is why, you know, if you're going to be using that, it's a good idea to take the radio and hold it away from you, hold the antenna away, grab a speaker microphone so that you can hold the radio up here. Because if you simply move it away from you and put it, you know, 0.6 meters away, look at that, it becomes safe. Interesting, right?
Had no idea.
Yeah.
Yep. Then that is actually one of the only times you will ever see, unless you're running like, you know, an antenna with 30 dB of gain, like a dish, and it's pointed right at somebody 25 feet away. You know, that'll always mess it up. So
this one's dangerous?
well, if you're running 5 watts and you're using it 100%, if you're using it 50% duty cycle and the antenna is right next to your head, I wouldn't do it. And I try not to, for that very reason. Any handheld radio can be dangerous, because if you're running low power, the answer is no. If you're running high power, the answer is possibly yes. And again, you're not going to cause yourself, you know, you're not going to give yourself like the equivalent of an X-ray, but it does cause tissue heating, because what do we know about RF energy? Energy is neither what?
Created nor destroyed.
Has to show up somewhere. So it causes heating of tissue, just like, you know, even if it's far, far away from microwaves, because a microwave oven is specifically designed to do that. This, you know, any frequency will do it some. All right.
Did you put that site link in the chat?
Oh, wait, I sent it. Hold on.
Yeah, I
There
was
we go.
gonna ask
Yeah,
that
yeah.
too.
Oops, there we go. Now I sent it to everybody.
Thank you.
Yeah, it got derailed. Okay, so now we are on to page number, what looks like 77 in the PDF. So we're going to make some tracks today, which is
That
good.
station setup and operating controls?
That is what we're doing. Okay, so station setup and operating controls. So basically what we've got is a transceiver. We're going to use transmitter receiver. That makes the word transceiver. We then have some sort of feed line that feeds into, if we have a tuner, which is an antenna tuner, which is an impedance matching device. Remember, impedance is kind of like resistance, except for RF, for AC. And we have a cable that goes up to here, which is your antenna. Now, feeding the transceiver, we have a power supply. And the reason we use a power supply is because transceivers are typically today designed for 12 watts DC, and our house power is 110 volts AC. So we have a power supply that converts 110 AC to 24 DC, and that connects to the transceiver. The reason that most of these radios are 12 volts DC is because they are designed to operate in a car. So they run off of 12 volts DC, besides the fact that power supplies can be big and heavy and take up space. So if you put it inside a radio, half the time you're not going to need it any. So here's your basic station design. Now, you can also have a computer. Computer is a very useful thing. Now, a computer can just be used for logging contacts. It can just be used for taking notes, but a computer can also interface with your transceiver. So you can have audio going across, back and forth. If it's computer audio, the computer audio out goes into the microphone in. And if it's if the computer is listening to the radio, the speaker output goes to the computer in. Very often, a lot of radios today will actually have a sound card built in, but that's not necessary to do. If you don't have a sound card built in, you might have an external sound card. Now, it's entirely possible that your computer will function with a sound card internally and you don't even need the external sound card. But I've done it multiple different ways. The other thing that your computer can do is, because something has to switch the radio from transmit to receive, this is known as the push to talk line. This is the same thing as on your handheld radio. You have that little button on the side that says push to talk. Basically, the computer will send a signal through computer control to the transceiver that switches it from receive to transmit. So this is just, go ahead. Okay. So the output of the transceiver is designed for 50 ohm impedance. Most cable that you get is 50 ohms, characteristic impedance. This cable is typically 50 ohms, but no guarantee. And the antenna is hopefully 50 ohms, but you don't really know. So what happens at this point is you basically have this antenna with a big unknown impedance in series with a 50 ohm cable. So the impedance that is seen by the tuner is question mark. Well, so it's 50 ohms on one side and question mark on the other side. So what you end up with internally, again, is a circuit that looks like this.
Is variable.
And this is going to be variable. And it allows you to basically trick the radio into thinking that it's looking into a 50 ohm load forever, in which case all the power goes out. What really happens on this side, and this is a very important distinction, let's say you have an impedance of 200 ohms in your antenna and 50 ohms in your cable. You actually have a 4-to-1 mismatch right here. You get a lot of reflection. Did anybody try tying the jump rope to the doorknob last night?
No.
No? Okay. Well, it's still a good exercise. So you still have a mismatch here, but what you end up with, again, is signals going up and down and reflecting back and forth. And this is fine for what we're doing. Eventually, all the power is going to go somewhere, right? However, if you run a TV station, this is definitely not okay, because what you end up with is every time you go up and down and up and down and up and down the cable, besides burning up power, maybe you're running 25,000 watts instead of 10 watts, you're also going to get ghosting on your picture. And then somebody will be complaining that your signal looks terrible. The picture looks terrible, and it's not their TV that's at fault. But so now the question is, if I have this system and I have my tuner set up so that my forward power is 100 watts and my reflected power, which it's going backwards, is 0, that means my radio is perfectly happy. All the power is going out as far as the radio is concerned. What's the SWR, the standing wave ratio, up here at the antenna? If I had a 4-to-1 mismatch before, what is it now?
2-to-1.
No, it's still 4-to-1.
Oh,
If it's 4-to-1, it's still 4-to-1. What the tuner does is it basically makes your radio happy.
oh, okay.
It doesn't fix the fundamental problem. The fundamental problem is still a fundamental problem, which is that you have a mismatch. And the worse the cable is, whoops, the worse the cable is, the worse it appears. So if I have a really bad mismatch, then what I have is power going up and down the cable multiple times. And the worse it is, the more heat is dissipated in the cable. So this really forces you to look at what you're using as feed line. So, and then we start having to look at decibel of loss per 100 feet. So a short cable, because it's per length, isn't going to be as bad as a long piece of cable. And lossy cable is going to be better than, it's going to be worse than good cable. So for feed line, I actually use an untuned antenna with cable that looks like this. This is known as ladder line. And this has an impedance of 450 ohms. So instead of 50 ohms, I use 450 ohm cable. Well, I know that I don't have a 450 ohm antenna. I still have that question mark. And right here, I have 450 ohms. I know that I have a mismatch. But at the same time, this cable, this feed line, is very, very low loss. So, on the order of like 0.2 dB per 100 feet. So I'm actually willing to accept that and keep and be okay with the fact that I have a mismatch because the loss is so low. So I don't really care. Yes.
Scott, a question.
Yep.
Your Viswar meter, did you put it between your tuner, I mean, between your transceiver and the antenna first, right? And
Yeah,
then you got a reading, a Viswar reading there.
and that's how you adjust your tuner.
But how did you figure out your antenna was off?
If I put a meter right here,
Yeah,
right? I can put a meter right there. I can take my SWR measurement there, and it doesn't matter what I do to my tuner. I can watch and see what's happening in the real world.
Okay, I was, yeah, okay. I was telling you originally without the tuner, you were doing your Viswar thing. But
Yeah.
okay, so you're saying the whole entity complete, that you're gonna see this mismatch because you're gonna get a misreading anyways. Okay.
Right. And Anna, you've got your hand up. I wasn't looking for a hand up. What's up?
So impedance is the resistance in alternating current, right?
Correct. It's
Okay.
it's how it resists the flow of alternating current.
Mhm.
Okay. Well, so this is a basic station setup. Yes.
I'm sorry. Go back a bit. The relationship between the power station, 110 AC to 24 DC,
Mhm.
but the transceiver is 12.
Oh,
volt
whoops.
DC.
Sorry. I'm so used to being at work. Everything at work is 24 volts.
Okay.
Thank you for that.
That's good, yeah.
Literally everything at work is 24 volts. We don't use 12 volts at work.
wow.
Well, not at my work, except if I'm doing mobile equipment, and most of the stuff I do is not. So, all right. Anything else there before we move on? Okay, here we go. Okay, so looking at our power connection for our system, why do we want to use short, heavy gauge wire for our DC power connections? And the answer is somebody's law. Whose law is it? Ohm's law. This is a really simple calculation, and we're going to show it like this. So if I have a 12-volt power supply, and I have a plus and a minus coming out of it, and it goes to my load, this is my transceiver. We'll call it like a resistor because it basically is. And this is going to be consuming 20 amps. All right. So if it's consuming 20 amps, that means that how much current is flowing right there through that wire?
Will be 20 amps.
Be 20 amps, right? Okay. So, and I've got this wire, which is not perfect. And there's another piece of wire here, which is not perfect. Let's say that the sum of all the resistance of all that wire is actually, I don't know, 0.1 ohms. So what we're going to do is make the assumption that we then have this wire that has 0.1 ohms in resistance, and we're going to put it as a lump of resistance right here. All right, and we have 20 amps going through it. How much voltage is dropped in that device? E equals I times R equals 20 times 0.1 is 2 volts. Now, 0.1 ohms does not seem like a lot, but if we only started with 12 and we measure across here, we have 2 volts loss. How much voltage is left for the radio?
10.
10 volts. What happens to the radio? What do you think happens to the radio?
Doesn't have enough.
It does, yeah, it's less power.
And actually, in some cases, it turns off. It actually, the lights go out and the radio goes off. So when you transmit and you key down the radio, the power goes out. Doesn't work real well. So if we look at a piece of wire, what are the things that affect its resistance?
Cross-sectional area.
Cross section. So we have the area. And what else?
Material construction.
Yep. What else?
Length.
The length. Okay. So how do you make its resistance lower? There are two ways to make it lower.
Shorten the length,
Yep. Shorten the length
bigger diameter.
and make it fatter. Yep. So if it's shorter and fat, if it's shorter length and it's fatter, the resistance goes down. And that's why we want to make as short a connection as possible. And we want to use as fat a wire as you can physically use to reduce the ohmic losses in the cable. Anna, I think you had your hand up again.
Yeah. So, I have a question. Can you go back to the diagram?
Okay. Well, which diagram?
The one you
This-
were just drawing, I mean.
Okay. Yep.
Well, so what is the transceiver? Like, what does that do?
Transceiver is your radio.
Okay.
I mean, it's basically got a transmitter and a receiver.
Okay.
And if you take those two words and mash them together, you get transceiver. And that's how we get the word transceiver. Okay. Okay, so moving on. Okay, so what is an appropriate power supply for a typical 50-watt mobile transceiver? Okay, so everybody, what is Ohm's law as far as power goes? Power is equal to what?
E times I.
E times I. Okay. I is 12 amps. What's our approximate? At 12 volts or so, how much current do we need to make about 50 watts?
4.
Right. Okay. So why is the answer a 12-volt power supply? What do you think? Well, as it turns out, there is something called efficiency. And in the act of making RF power, depending on the amplifier that you use, efficiency is equal to power out divided by power in. So if we're making RF power, in order to make, let's say, 1 watt, if we have 50% efficiency, how much power would we need in?
50.
Now if we have 50%, let's say we have 50%, we have 2 watts. So we would need 2 watts in to make 1 watt out. So if we're running 50 watts out at 50% efficiency, we would need 100 watts in. So if we're doing that, and we said we need typically 4 amps, well, we just doubled it. We would need at least 8 amps. And let's say that you have a transceiver which looks like this. Da, da, da. Let's say your transceiver looks like this. Okay. And okay, so let's ask a question here. What do you notice about this transceiver? Is there a display?
Yes.
Yeah.
Okay.
Yes.
What power is the display?
50 watts.
No. Well, I mean, what power is the display?
Oh,
If it's not plugged into a power supply, does the display work?
No.
Yeah, it's a battery.
Battery.
Well, no, it's not. It's not plugged in. This is a 50-watt radio, so it is.
AC.
It's plugged into 12 volts DC. So if you're listening to it and the speaker is making sound, what's powering that speaker?
Battery.
Well, again, yeah, I mean, when
12
you say battery,
volts?
it's a car battery. Yeah, it's 12 volt. Okay, so let's see. How do you know what frequency it's on?
Tells you.
The
It tells
display
you.
will tell you.
Right? And what's powering the display? What's powering the number on the display?
12 volts. 12 volts.
And through what?
A resistor.
Well, what's running inside this thing that's putting a number on the display?
The current?
No. Well, yes, but what's actually running this radio?
A computer.
A
Your
computer.
battery.
A computer,
Oh,
right? Because it's putting a number on the display. So what's running the computer?
your battery.
That's right. So all those things figure into what it takes to run something. Even if you're not putting out any power, this radio is still going to be requiring, let's say, 15, 20 watts of power just to keep the lights on, just to keep the display lit, because it's got a backlight. So what powers the backlight?
Again, it's your battery.
That's right. So yeah, exactly. And there's also typically lighting in the microphone behind the buttons so that when you're driving at night, you can see the buttons. You don't have to fumble and wonder what you're pressing. So what's powering that?
You,
Diode.
your battery.
Yeah,
Battery.
yeah, power, right? So power in, is it power in
Equals
translates
power
to power
out.
out. Everything that makes noise or lights up or anything requires energy, right? So that's why you have that's why something like this requires more power to run than you think it will. And
Hey,
that's
Scott?
why, yes,
You got a picture of an old tube amp or tube transmitter?
sure. Absolutely. Let's go with an SB 303. Here we go.
So is that
Let me put that up there.
that radio that you displayed, is that something that you own or you
No.
recommend?
They're all fine. I mean, almost anything you get these days is fine. We'll go into that a little bit. So notice, okay, you wanted to see like an SB 303, a tube rig.
Well, or just, yeah, so you can see the tubes. I mean, tubes make so much heat. It's a great analogy.
Yeah. How about a 3500Z tube
Yeah, there you go.
lit up? Like that.
Yeah.
Yes, it's called thermionic emission. It takes power just to light up the tubes. And that's why the
And they're still available to get the tubes.
tubes are that people tried to eliminate them for years. And,
Right.
And yeah, you can still get power tubes.
Okay.
All right. And that's why the answer for a 50-watt power supply is kind of a trick, because it's 13.8 volts at 12 amps. And again, because of efficiency and keeping the computer on and the lighting and stuff like that. Okay. Yes.
I still don't understand the power in and out.
Okay. So, okay, here's the easiest way to think about it. All right. All right. Take your hands. All right. You got your hands like this?
Yeah.
Okay. Rub them back and forth. Do you see your hands moving?
Yeah.
Okay. What do you also notice about your hands?
There's friction.
There's friction. And what's it doing?
It's resisting.
It's making your hands warm, right?
Yeah.
Okay. What is warm? What is heat? Another way of saying heat is another form. Heat is another form of energy, right? So if you just put your hands in the air and move them up and down, would you feel it? Would you feel the heat?
No.
No, but if you put them together, you have friction, right?
Uh-huh.
So which do you think is a more efficient way to move your hands up and down? Touching or not?
Touching.
I don't think
no,
so.
Not touching.
Because you're
Because there's
wasting energy
Yeah.
by heating them up. That's efficiency. So
Can you
which,
give can you give us another problem like
Have a fork.
I was thinking it might be.
to like work out?
yeah,
'Cause
sure. Okay. So
I
let's
just
say,
that part.
okay, so let's say you found that in order to run a, let's
Hey
say,
Dad, can I have time?
let's say you were running a radio and it was putting out 100 watts of RF.
Mhm.
That was the output that you measured, right? And then you also went over to your power supply and you said your power supply is running 13.8 volts. And it was at that time that it was putting out 100 watts of RF. It was producing 20 amps of current.
Mhm.
What is the power that's being produced? What's the formula for power? P is
Formula
equal
for
to,
power is power equals current times energy
or voltage,
Voltage.
right?
voltage.
Okay, so that's 20 times 13.8
Mhm.
is 276 watts. And how much power is being made going out through the antenna?
100 watts.
Okay, so efficiency is power out divided by power in, which is, what's the power out?
276 watts.
No, that's the power in.
Oh,
Because
100 watts.
here's the power supply. And it's feeding DC power into the radio. And the out is going up, what's going up to the antenna.
Mhm.
So this is your in and this is your out. So your power out is 100 watts
100 watts.
and power in is,
276 watts.
okay, and 100 divided by 276 is, let's see, divided by 276 is 0.362,
Okay.
which is 36.2%. That's your efficiency.
Okay.
Scott, I've got a quick question. I know this I know this is probably based on various factors, but I suppose on average, the most common house stationary radio setup, how many watts is that pulling?
Well, how many watts is it gonna, I mean, it depends on the size of the transmitter. I mean, a typical 100-watt radio will pull about 22 amps at full power at 12 volts.
Okay.
So, but if you look at how much that actually requires to make it when it's plugged into the wall, typically, 110 volts at like 3 amps.
Gotcha. Thank you.
Okay. What are your connections between your computer and your radio? You have receive audio, transmit audio, and transmitter keying, as we discussed. How do you make your radio work with a computer? Well, you have software running this thing called FT8. We were looking at that yesterday. It showed an entire range of signals in one little audio passband on the screen. Basically, the audio input and output of a computer running WS-JTX software is required to send it. Basically, the computer is doing the job of you. Which of the following connections is made between a computer and a transceiver to use computer software when operating digital modes? Computer line in. So basically that's received audio on the computer going to the transceiver speaker. Now you could also say that computer line out goes to the microphone jack. Basically, audio goes out of one and into the other, and then out of that one and back into the first one. There's something called a ferrite choke. A ferrite choke is basically a donut made of a powdered iron compound or nickel or something. Manganese is sometimes used for it. And it's basically a hollow shaped donut that's made of iron powder and nickel powder and glue baked into a shape. And you run your cable through this So any cable that has current flowing, well, what does a current make? If a current is flowing, what does that make?
Electromagnetic field.
In particular, what kind of field? Not electromagnetic.
Magnetic.
A magnetic field. Okay. Has anybody ever seen like an iron magnet? Probably, right? Iron is known as a ferromagnetic material, and it's used as the basis, nickel, iron, and stuff. Those are really good for magnetism because of the structure of iron. So what we do is we take a donut, basically, and we run our wire through the donut. And if there's any DC, that's okay. But if there's any AC, it makes a magnetic field that goes back and forth and back and forth. And what happens is that this material tends to constrain magnetic fields, especially alternating magnetic fields, and it gets warm. And if it gets warm, it's basically dissipating the magnetic field energy. So you might have some current flowing over here, but when you get over here, it's not flowing anymore because the energy is essentially burned up. So that is how we keep hum and other signals, alternating current signals that we don't want, in particular at radio frequencies, off of microphone cables. And this is known as a ferrite choke. You may have seen one of these. Does anybody have a computer power supply that they're using?
Yeah.
Okay. So has anybody ever seen one of these things on their computer power supply cable?
I believe so.
Yes.
That is a ferrite choke. That's a ferrite choke right there.
Okay.
So basically, if there's any,
Really?
if there's any RF energy on your cable, it'll exist on this side, and once it hits the choke, it goes away before going into your computer.
Oh.
That's why it's there.
That makes sense, since the most of the magnetic changes are on the surface of the cable.
Yep. There you go. Practical use. Okay. And also different ferromagnetic materials. If you start to look at what makes what's known as a ferrite, if you look up a company called Fairrite, Fairrite, you will see that they make probably 100 different mixes that react differently at different temperatures, different frequencies, different power levels, different shapes. They make literally thousands of different ferrite materials. Because if you look at electronics, there's all kinds of stuff. There's circuit board size. There's, ferrite chokes that are this big. Sometimes you can use them as the basis for a transformer if it's exactly what you want it to look like. Sometimes you have to put a big fat cable through it. Sometimes you get a really, really small magnet wire and you wrap it through it 1,000 times. So it all depends what it's being used for. Okay, let's see. So that's ferromagnetics. Who would have thought that it would be so interesting, right? And basically it's just like, making a cake. You have a recipe that you follow, determines what you put in and how much glue you use. Okay, which of the following conductors is preferred for bonding at RF? Okay, so what we're going to do a little bit right now is discuss the difference between RF and we're going to discuss the difference between RF and DC. So let us say that we have a piece of equipment right here. Right? And we are going to have a ground bus over here. And what is ground, everybody? What is the definition of ground?
Zero potential energy.
0 volts. That's right. Zero potential. So typically what we do for that is we take an 8-foot rod and we pound it into the ground. So our voltage here is at 0 volts. Okay, so we're going to have 2 different kinds of ground. We're going to have this ground and we're going to have this ground. This one is power ground or safety ground. And this one is going to be RF ground. Okay, so now, if we're going to have safety ground, what frequency is our wall voltage operating at? How many hertz?
60.
60 hertz. So how about RF ground when we're transmitting? How many hertz?
Depends on the transmitter.
Yeah, but let's say at least 1 million hertz, at least.
Wow.
Right? Well, that's 1 megahertz. That's what we do. So now the question is, what is the wavelength of 60 hertz? The wavelength of 60 hertz is about 5 million meters, or about from here to from the west, from the Atlantic Ocean to the Pacific Ocean. That's one wavelength at AC power. However, at 1 megahertz, it's about 300 meters. And depending on the band you're on, it's considerably shorter. This could be down to, let's say, 1 meter. So that which makes a good ground at power does not necessarily make a good ground at RF. Because if you have 0 volts right here and 0 volts right here, what you might find is that, well, if you're at 0 volts here on your power ground, because the wavelength is so long, yeah, you're going to be at 0 volts on your case, on your equipment case, and you won't get a shock. But if this cable, let's say you're operating on a wavelength of 1 meter, and this cable is 7 meters long, how many waves can you draw on this cable by the time you get there?
7.
Yeah, that's a lot of wavelengths, right? So let's say that it's such that your sine wave that you're drawing, by the time you get there, is no longer at 0. Well, if your sine wave is no longer at 0, right? What does that mean for your what you would call ground? You expect ground to be at 0 volts, right? Well, you started at 0, and now it's up here. Is that at 0 volts?
No.
No, it's not.
No.
So in other words, it's not really a very good ground. So power ground and RF ground are completely different things.
Different.
They are different. So for RF grounding, you want those, for power ground, you know, it can be anywhere within 100 feet. You'll be okay. 1,000 feet, you'll still be okay. For RF ground, you want those connections to be really, really short, so that at most you have whatever frequency you're on, a fraction of a wavelength, if at all possible. Now, the other thing that's tricky about this is if I were to draw this conductor and I look at the cross-sectional area of this conductor, DC distributes throughout the cross-section. But if I were to draw AC, what I would find is that there is something called the skin effect. And what the skin effect does is that it forces the current to flow out toward the surface of the conductor, not in the center. It forces it out toward the surface. The higher the frequency, the greater the distribution of current on the surface of the conductor. To the point where, you know, at RF frequencies, you basically have no current flowing in the middle. It's almost exclusively flowing on the outside. And again, this is called the skin effect. And what's interesting about this is that if you look at a conductor, how well does at RF a hollow conductor work? It's great. It actually is fine because you don't use the middle of it anyway.
Right.
Isn't that weird? And on
Yeah.
top of that, if we look at this, how many conducting surfaces are there on a hollow conductor?
Less. less resistance.
Actually, how many conducting surfaces? There's actually two. You can actually have different currents flowing on the inside and the outside. Which is really kind of profound, because if you do that, so let me ask this question. Let's draw a piece of coaxial cable. All right, so we have our shield and we have our center conductor. How many
Scott?
yes,
I'm sorry. Random question. What software are you using to do all your drawing?
it's just Zoom's it's just Zoom's whiteboard function.
Oh, cool. Thanks.
So, okay, how many conducting surfaces do you see here?
Two.
Ah, that's not two. One.
Great.
Two is on the
The
inside
face.
and three on the outside. So you actually, because
Three?
the shield is not infinitely thin, you actually have potentially three different surfaces. And in fact, you have a match between the inside, but between the center conductor and the inside conduction surface of the coaxial cable. And then on the outside, you have potentially another surface that can carry current.
Wow.
Yes. And this is why, if you think about this, since those currents are different and the inside and the center conductor and the inside of the shield match, this is why we can actually do something called an RF choke on a piece of coaxial cable. So here's our coaxial cable, and we can actually put an RF choke, one of those donuts, around a piece of coaxial cable, and that does not affect what's happening on the inside. But what it does do is, if there's anything flowing on the outside, that will basically absorb the energy flowing on the outside. Isn't that a trip? Because of this thing called the skin effect. Okay, so now the question is, if we want to have good bonding at radio frequencies because of the skin effect, would we use round wire or flat wire, given that it all flows on what we consider to be the surface? What, for the same amount of material, what provides us the most surface?
Flat wire.
Flat wire. So we basically take we take our copper wire and we pound it into a sheet. And that actually is a better RF conductor. So that's for bonding at RF, we use flat copper strap, because surface area is the best part.
All the more expensive pieces.
Yeah. It's not that bad. Where should the negative power return of a mobile transceiver be connected in a car?
Directly to the battery.
Directly to the battery. And why is that? Because if you think about it, your entire car is actually only, it actually assumes that the entire frame of the car is grounded. Why can't you just go to a chassis panel? I mean, they do it for a lot of lighting. They don't, they assume, well, here's your car, and you have your car like this. And here's the battery. It has a plus and a minus, and the plus is distributed to back here. You have your lights, and there's a fuel pump, and there's an ignition system, and the ground part of the system just basically goes to this panel and this panel and this panel and this panel and this panel. And basically, if you have this light back here, you just basically run it to there. Why don't we do that with a 20-watt radio, or sorry, a 20-amp radio?
To avoid ground loops.
To avoid ground loops, and the fact that how is a car actually put together?
Oh, modular. Yeah.
We have things that are welded together.
Right.
Is any auto manufacturer assuming that the welds that they did are necessarily going to be able to handle 20 amps DC?
Right.
I don't know. I didn't build the car. I don't think they probably planned on that. So if I had a radio back here and the ground is carrying 20 amps DC back to the battery, is that a good ground path? I don't know. The best way for me to do a ground path would basically be to just run a big fat cable back to the battery.
A lot of new cars are aluminum and they are bonded, so they're not
Yeah.
even welded. So
Yeah, there you go. They're not necessarily designed to handle that much current. So because of that, we don't do that. We just go straight back to the battery.
You know, another interesting thing about new cars is that the batteries are getting smaller.
Yeah.
You know, because I don't know the reasons, but you know, you don't get the big giant batteries, and they're also AGM batteries, which are much more expensive.
You know, that's actually what I use in my own shack. I have a backup battery for my whole station, and it's an AGM, which is, by the way, that's an absorbed glass mat battery, by the way, for anyone who's curious. It's not a wet cell. It's a gelled electrolyte lead acid battery.
Question, Scott,
they're actually better for deep cycle.
And you don't want to spill sulfuric acid in your shack.
That's true. Go ahead, Mark.
yeah, I just want to ask, because we're so grounding and bonding, two different topics altogether, right?
Yep.
And because I learned that pretty quick when I was putting in a pool light.
Yeah. Well, I mean, grounding and
putting
bonding
in a pool light, your bonding becomes.
That's a safety issue. Yeah. So, I mean, safety ground, it's basically comes down to the difference between safety ground and RF ground.
Right. Okay. Thanks.
Safety ground is to keep people from dying. RF ground is to keep giving RF a nice clean path to run. And not like I once leaned up against the microphone and got an RF shock on my lip. It didn't feel great. Where does ham shack come from? I don't know. My ham shack is in the back of my garage, so it's kind of like way back in the shack. You know, it's way back. It is a shack, literally. Let's see. How can you determine the length of time that equipment can be run off of a battery? Well, you have something called an amp hour rating. So batteries come in either watt hours or amp hours. That's amps times hours. So if I have a 5 amp hour battery, that means I can draw 1 amp for 5 hours, or in theory, 5 amps for 1 hour. If I have a 100 amp hour battery, that would be 20 amps for 5 hours, or 100 amps for 1 hour, but that's not advisable, or 1 amp for 100 hours. So divide the watt hour rating by the peak power consumption, and that's not right. Divide the battery amp hour rating by the average current draw, and that gives you time. So it's amps times time. All right, operating controls. What is the effect of excessive microphone gain? This is effectively too much audio gain. What does everybody hear?
Noise.
Yeah,
Noise.
you basically you get distortion, right? It's driving the amplifier beyond its ability to amplify cleanly. The result of tuning an FM receiver above or below a signal's frequency, that basically ends up with distortion. You're basically off frequency. A VFO knob. How do you enter a frequency? What we're going to do is go back to our web SDR, and we're going to play a little bit with this. Here's our web SDR. So this is basically a modern day tuning knob. Notice that there's a slider and there's a frequency, and I am adjusting the tuning knob. I want to change the frequency. I can come down to another frequency. There could actually be a tuning knob where I would spin the knob and the number would change, or the slider would change. I can also come down here and directly enter it, 14020. and it goes to a different frequency.
Now, this website you're at can anybody get on this?
You go to websdr.org and pick your favorite SDR either near you or far away from you. It's a great tool for practicing.
It was really wild to watch the web SDR in Ukraine right as the Russians moved in.
Yeah. You know what else is really crazy? Transmitting and listening to yourself on a web SDR somewhere else. You can actually listen to yourself.
It's amazing.
See how you sound somewhere else in the world. A way to enter a favorite frequency or channel on a transceiver, you store it in a memory channel, punch up memory channel 22, and it goes back to right where it was. The scanning function in an FM transceiver allows you to scan through a bunch of frequencies. Squelch. Okay, so let's see if this thing has squelch. I hope this thing has squelch. And so we're going to do this, and we're going to turn on squelch. There's our squelch. So what does squelch do? If there's nothing to be heard,
It's quiet.
Quiets it
It's
down.
quiet.
Yep, that's squelch.
Yeah.
How do you turn on keyboard controls for moving the frequency, like fine tuning it?
On what? This thing?
On web SDR. Yeah, I was trying to play with.
I think it's just up and down. So if you go here, right here. Plus and minus.
Oh, okay.
Okay, it's the other thing you can do. Let me quiet this down. How can you adjust squelch so that a weak FM signal can be heard? The easiest way to describe this is if I go over to my handheld radio and I do this. I turn the squelch completely off so I can hear stuff that's way down in the noise. If I turn the squelch on, there's nothing to be heard. Repeater offset. Okay, so part of this now is going through and describing what a repeater is and does. Okay, so here is a repeater. This is the schematic drawing, essentially black box drawing of a repeater. We have a receiver, and we have a transmitter, and we have a controller. The controller basically handles the audio that's being received. So the receiver is connected to an antenna, and the transmitter is connected to a different antenna. The controller decides whether what's coming into the receiver is forwarded to the transmitter and goes out through the transmit antenna. That's a receiver controller. And this is basically how a repeater works. Now, can anybody see any issues or other things that I might need to draw here? Well, we might need to say, okay, well, this receives signals on, let's say, 2 meters and transmits out on 70 centimeters. If you look at your frequency allocation charts, you will see that this is, let's say, 146 megahertz. And this is 438 megahertz. This is actually how the repeater on board the International Space Station works. These frequencies are far enough apart that they typically don't interfere with each other. So you don't really need any kind of special hardware to do this. However,
what about harmonics?
Yeah, you could, but the FCC rules require that harmonics are down at least 60 or 70 dB.
Okay.
So not too big of an issue.
Okay.
Also, given the fact that it's retransmitted on this frequency, then this is, 2 meters is going in and 438 is going out.
Mm-hmm.
There's very little chance that anything from the ground is going to affect anything, and that 438 will never get back into 146.
Okay.
So that's not an issue. So this is typically like, and this is a good chance for me to bring this up. Can everybody see this right here?
Yeah.
satellite picture?
That's the
Nope.
balloon, right?
Nope.
The balloon that got shot down?
Nope.
Space station?
I'm going to take it out of the bag.
What is that, like QSL card?
That is a QSL card. I'm going to take it out of its wrapper because I have it protected.
So you got a QSL card from the ISIS space station.
Yep. There you
Wow.
go. So there's the QSL card. Notice the call NA1SS.
Congrats.
And here's the information. On field day last year, I was standing out on my back deck with 2 radios, just like this. I had a tape measure Yagi pointed up on 2 meters, and I was listening on 70 centimeters with another radio. And not only did I hear myself, but I actually talked to Shel Lindgren, who is an astronaut up there, who was working from the space station on field day. Made a contact with an astronaut.
That's cool.
One of the high points of my ham radio life. And then I, of course, asked for a card, and I got a card. So the way that it works is that you have, again, here's the receiver, 2 antennas. We have a receiver, and we have a transmitter, and we have a controller right here in between them. The controller is responsible for IDing the station, because every station has to be identified. You usually have a Morse code ID. So that gets injected into the signal going out. So what happens here is that people all over the place transmit on a specified frequency. And if the signal that is received by the repeater controller matches the criteria necessary as defined in the controller, the signal will be retransmitted out through the transmitter and go out to the world. So the published frequency of a repeater is usually its transmit frequency. So in this case, we're going to use the Valley Club, 146.72 megahertz. And we have something called a repeater offset. This is also something that's published. The offset in this case is negative 600 kilohertz, which means that the repeater will be listening on 146.72 minus 0.6, which is 146.12 megahertz. So that is the frequency that it will be listening to. If then there's also something called a CTCSS code, or a squelch code. It's listening for, in this case, 100.0 hertz as an audio tone. That gets picked up here. If it matches, then the signal says, yep, okay, we're going to send it out and forward it along. And if it's not there, then it doesn't get resent. However, now if it does match all the criteria, so in other words, you matched the desired offset and you matched the desired squelch, what happens is that your signal is then retransmitted as if you were on top of the repeater, on top of that mountaintop where the repeater is located, which is great because you might be transmitting from somewhere where you have a 1-watt handheld radio and you're down in a valley. But the repeater is at 3,500 feet on top of a mountaintop. And then you're being retransmitted, your signal is being retransmitted as if you were on top of a mountaintop at 3,500 feet. And everybody who can see that mountaintop, that could be 100 miles away, can hear you, and vice versa. So you can have a conversation a great, great distance away, just using a handheld radio. And that's where the power of the FM repeater is really, really useful, especially in areas where we've got, a lot of mountains, like
Hey,
Oregon.
Scott?
Yes.
How do you avoid like overcrowding on a repeater where everybody's trying to use it at the same time?
You either run a round robin, you run like a round table discussion where everybody knows what's going on, and you say, okay, I'm done talking, I'm going to hand it over to this person. And then that person's done, and they're going to hand it over to this person. And so you just sort of learn how to do it.
But basically, the repeaters only have one receive transmit channel pair.
Yep.
To work with.
Yep. Now, the other question is, how do you keep the peace as far as not repeaters not interfering with each other? So in Oregon, we have something called the ORRC. We're going to get into this a little bit later too. So we have these things called coordinations. These are all the repeaters in the state of Oregon. And the ORRC will talk to that responsible in Southern Washington and Northern California to make sure that even across state lines, because radio waves don't care about state lines or international borders, that we don't interfere with each other. So all of these, if you want to put up a repeater, you get with ORRC and make sure that their maps say that you're not going to interfere with another repeater on the same frequency somewhere else. So the repeater that we have on 146.72, notice that there are 2 repeaters in the state of Oregon that are on 146.72. One is in Junction City, that's the one I'm the trustee of, and the other one is way up on a hilltop in Astoria. On a very rare day, we can hear each other. We can hear both of them. But it's a very rare day. And on top of that,
the output frequencies or the input frequencies?
Those are, well, these are the output frequency, 146.72, and 146.12 is the input frequency. And that basically generates the offset.
Mm-hmm. What does it cost? What does a repeater cost? A station?
Well, it depends what band you're on, how much power you're running. I mean, a lot of mobile radios can actually function as crossband repeaters. The toughest part is making sure that they ID legally, because they have to actually transmit their CW ID.
Hey, Scott.
Yeah.
You gave us a demonstration yesterday. You said the repeater was 35 miles away.
Yep.
And you picked up your friend.
Yep.
It was pretty cool.
Yep.
Yeah,
Actually,
I think you also said it was somewhere around $4,700 for that repeater.
No, well, it depends. That was just for the filtering.
Yeah.
So the reason that it gets so expensive when you do that is because you have, let's say you have your repeater again, and it's entirely possible you're going to be using the same antenna for receive and transmit, for one thing. And unlike up on the ISS, you're on 146.12 in and 146.72 going out. And this is going to be running like 100 watts. And that could actually be the exact same repeater. So in the RF path, you have to have something to make sure that these do not interfere with each other. In particular, if you have a signal that goes like this, let's say they're using the same antenna to make sure that one frequency goes down and the other one goes up, but they're on the same band. And you have 100 watts going out. So if you have 100 watts going out, how do you make sure that none of it gets down into the receiver?
Mm.
And that is, you have a really, really, really tight cavity filter that has, a pass band going out and a reject going in, so that only 146.12 goes that way and 146.72 can only go that way. Very, very, very narrow filters, and thus expensive. Okay, let's see. Where were we? Okay, that's repeater offset. Repeater offset is the differential between receive and transmit. What function is performed with a transceiver and digital hotspot? That would be communication via digital voice or data systems with the internet. We use something called Echolink. There's also something called a talk group. Talk group this is actually a DMR handheld that I have right here, digital mobile radio. It's a little bit, well, it looks like a handheld radio, except that in addition to talking analog, can actually talk over digital repeaters. So it can do digital audio. You have multiple talk groups when you're dealing with that. And digital repeaters can actually be connected over the internet. So people who are part of a talk group can be distributed locally or over the internet. So you basically will specify, I'm on a digital repeater and a part of this talk group, and everybody who is a part of that group will receive signals from everybody else on that group and nobody else. A code plug, how a digital radio is programmed to function is known as its code plug. So it's access information for repeaters and talk groups. That's called a code plug. I don't know why it's called that. I've asked lots of times. Nobody can really tell me. How is a specific group of stations selected on a digital voice transceiver? You enter the group's identification code. Sometimes it'll have a name. Sometimes it'll be a color. Red group, blue group. The purpose of the color code is to establish groups of users. D-Star is ICOM's company-specific protocol for digital communications. D-Star, in addition to transmitting voice, transmits data. So you actually have to, oh, hold on.
Hey, Scott.
Yeah, I hear there we go.
So you're a controls guy, Scott, right?
Yep.
So do you know the other company that was also named ICOM?
I do not.
So in the Alan Bradley world, the original DOS software for programming Alan Bradley PLCs was a company called ICOM.
Oh, God. that goes back a ways.
Well, I go back a ways, you know.
That was before my time, believe it or not.
That's where Rockwell Software came from, because Alan Bradley
bought it.
Company.
Okay, that makes sense. They buy everything. Okay, let's see. So D-Star is digital as well as voice, or digital data as well as voice. So you have to put your call sign in. We are on page 83, by the way. Multiple receive bandwidth choices on a multi-mode transceiver. We were listening to that just a minute ago on WebSDR. You can select wide or narrow. So you basically select the bandwidth that matches what you're listening to, so you can reject everything else. If you're on single sideband is about 3,000 hertz wide, or 3 kilohertz, so 2,400 hertz is a good filter for it. For Morse code, a 500 hertz filter is an appropriate bandwidth. You can actually go narrower and narrower and narrower if you want. There's another something called an RIT, which is receiver incremental tuning, and that allows you to change a receiver frequency without changing the transmit frequency. Usually they are linked together. It allows you to sort of separate them. The reason you would want to do that is because the other person you're talking to, their radio might not be completely accurate as far as frequency goes. And if that's the case, then they might be slightly off frequency. And this is what being slightly off frequency sounds like. Can anyone understand that? So if you are on frequency and that's how they sound, you might want to have that. You might want to have that clarifier, the receiver incremental tuning, so you can adjust it accordingly without changing your transmit frequency and thus sounding weird to them. Now, this is the sound of listening on the wrong sideband. Can anybody understand that? Me neither. Okay. So now we can make this wider. Notice what happens if we make it wide. Notice there's a lot of extra hiss and stuff. That's why we pick an appropriate passband. Notice what happens if we make it too narrow. You can't pick up enough of the information to hear it. However, we can use this same passband, make it nice and narrow, go down to Morse code. Since it's a much narrower bandwidth signal, sounds just fine. We can even go narrower.
This really is amazing technology. I mean, you could almost dispense with a receiver with that.
Could, yeah, almost. But what fun would that be?
Yeah.
Okay.
Scott,
Yeah.
is there a machine that can decipher into text what
Yes.
Morse code is?
Yes.
Okay.
There's actually, well, when you say machines, it's basically software.
Yeah.
Yeah.
Now, the tricky thing is that unlike other digital codes that are sent largely by machine, a lot of people like myself still send Morse code by hand. And what happens is everybody has a little bit different timing up here. Right? There's a specification that says that a dit and a da, the da is 3 times longer than a dit, and the spacing between a dit and a da in a letter is 1 unit, and a dit is 1 unit, and a da is 3 units, and the spacing between letters is 3 units, and the spacing between words is 7 units. Right? Now, not everybody does exactly that, and people send, unlike digital modes, people also send at different speeds, which means that it's sometimes really hard for that software to lock on because it's trying to deal with, human inconsistencies.
Speeding up, slowing down.
Yep, exactly. Okay, so somebody said let's dive a little deeper. I want to make sure that we finish, but let's dive a little deeper into sideband. Okay. So, what we have is a frequency from 0 to infinity, and we're going to pick something called a center frequency right here. This is what AM looks like, amplitude modulation. Over a period of time, an AM signal in time would look like this. It has a carrier frequency, which is a very high radio frequency. So that inside is known as the carrier, and outside is called the envelope. This is the modulating frequency, the signal that puts information on it. It basically shapes the carrier amplitude. That's why it's called amplitude modulation. The overall picture of this is that you have the center frequency of the carrier, so that's FC, and then you have these things called sidebands. The sidebands represent the information that is being used to modulate it, and that's what AM actually looks like, and that's what we were seeing on that waterfall display. What we do with sideband is say, okay, well, how much information is in the carrier? This has 0 information. Nothing. So with AM, the more modulation we have, the lower the carrier gets. It's basically just a marker, though. So if we're transmitting it, since it has no information whatsoever, what we can do is say we're smarter than it is, and we can just basically eliminate it. We don't have to send it. Somebody will reinsert it when it gets to the other side. We'll be fine. Then we also know that this is called the lower sideband because it's on the lower side, and this is on the upper sideband because it's on the upper side. Well, as it turns out, this is the upper and the lower. Well, upper and lower are just mirror images of each other. So if we pick one, we can basically say, well, I'm not going to waste the power to transmit the other one. I'll just transmit the upper, or I'll just transmit the lower. So now what we know is that our reference frequency, when we go to receive it, it had better be right here because we have to reinsert it. If we are off frequency, it will sound wrong.
Yeah.
And that's why it's important to pick our center frequency when we're listening to single sideband, or else they sound like either a monster or Mickey Mouse.
Yeah.
So now we have our upper sideband frequency, upper sideband signal. We send just our one sideband. It gets received on the other end, and its efficiency goes way up compared to AM, and it only fills up 3 kilohertz instead of previously what was 6+ kilohertz. So it's more energy efficient and it's more bandwidth efficient. Now, if we start looking at other modes, like an equivalent you know, a Morse code signal will maybe be that big. A digital signal will maybe be only this big. And the reason that I drew them taller is because you still have the same amount of transmitter power. So if you take your same amount of transmitter power and you use it to fill up this entire space, maybe your Morse code signal is actually this tall, which means that it gets through the noise. Let's say that at the other end, the noise level is right here. The Morse code signal pops up through. The same thing with the digital signal. It might be, because it's even narrower, you can make it this tall, which means that the voice signal is the first one to go, right? Then you start losing your Morse code signals, then you start losing your digital signals.
Hey, Scott,
Yep.
on a SSB receiver, is it basically receiving that single sideband and then creating an inverted image of it and combining it so you kind of build a, how does that work?
So what you do is, what you do with single sideband is you have this signal coming in that looks like this, and then you give it a reference frequency right here.
Yep.
Right? And you then take it, and the way that this works is you have something that we're going to get to in a minute called a mixer, which is a nonlinear combiner of two different things. So you have your input signal, and then you have a thing called a beat frequency oscillator. And a beat frequency oscillator, basically what it does is it combines these two signals and produces a new third signal. And we're going to take a break, but what I'm going to do is show you something called a beat frequency that will hopefully explain some of this.
So technically the mixer adds the two signals together.
It not really. Yes and no. It does, but it actually does more. It does a, like if this is A and B, it does A plus B, A minus B, B minus A, 2A, 3A, 2B, 3B. It makes a horrible mess of stuff. And then it sums and differences. So if you're looking for this one thing coming out, you've got all this other stuff. So what do you think you would put after a mixer to make sure you only get this one? What would you use? You would use a filter. There we go. Tuned components. And if you've built your receiver so that you can tune the beat frequency oscillator to different frequencies, you can actually build your filter so that it's at a fixed frequency and just retune your BFO so you change the output.
So the BFO knob on a receiver, typical receiver, is actually changing the beat frequency.
It's changing the beat frequency oscillator position. Yes.
So it's a variable frequency oscillator.
Yep.
Okay.
Everybody ready for a 5-minute break?
Yeah.
I know I am.
Jesus.
You doing okay?
No. That's intense shit. He's a 13 and he made fire. Jesus Christ.
Hey, Jeff, your mic is still hot.
I don't know which is harder, the material or sitting there for so many hours.
Hey, Jeff, your mic is still hot.
I'm comfortable. I'm curious why he didn't explain modulation as multiplication.
That's only true if it's an amplitude modulated system, not FM. Right?
Hey, all right, what was the question?
Somebody asked about modulation being equivalent to amplification.
It's totally different.
Modulation is for AM, I think it's multiplying the carrier frequency by the audio signal.
Yeah. But it's different for, I mean, if you want to think about it, modulation is just modification of one signal by another signal to put information
Right.
on it.
Yeah, you can do it a whole number of ways, like amplitude modulation, frequency modulation, phase shift,
Yeah.
on and on.
You want to hear you want to hear what a beat frequency sounds like?
Sure.
Okay, here we go. Can everybody hear that?
Why would we want to listen to it for 8 hours?
You wouldn't. Well, but let's say you're using it for something. So here's my question. What's the point of understanding that beat frequency? What would be the point of us trying to understand that beat frequency? So
See how one frequency will be involved changing another.
yeah, so here's 432 hertz. What does everybody hear?
432.
Owl.
Just a sine wave, right?
Constant.
Here's 440. All right, they sound almost the same, right? In fact, what is the difference between 432 and 440?
Just frequency, not amplitude.
That's right. And it's specifically 8 hertz, right? When you beat the two against each other, what you will find is that if you add them together, such as happens in a mixer, basically I'm making a cheapo mixer right here. Here's one frequency. Here's another one.
Oh, wow.
Do you notice the underlying warble?
Yes.
Interfere.
The really annoying warble? If these were perfectly matched, you would not hear that. If these were off by 1 hertz, if you had 439 and 440, how often do you think it would warble against each other?
1 second.
It
Every
would be
second.
every second, that's right. And if it were 2 hertz off,
Every 2 seconds.
it would be it would be twice per second.
Twice?
Right?
Oh,
Right.
right. It's inverse. Right.
Right? So what's interesting about this is that this is how a beat frequency oscillator works. The difference between the two frequencies, let's say that 440, which is this one, is our beat frequency. That's the one that we're injecting. And the one that's coming in out of the atmosphere is this one. Somebody on the other end has taken this one, and normally they would have been putting out 440, but for the sake of argument, what they did is say, well, okay, our dial is tuned to 440, but because of the information that we want to put on the signal, instead, the signal that we're putting out is now at 432. So match your signal to 440 and listen to what you get. Ideally, that is the same thing that is happening with single sideband. When we generate, or Morse code for that matter, when we generate a sideband that looks like this is the center frequency. If we were to match that, what would we get? We'd get just one pitch. But if we look at the stuff that they're putting on, like if the other station were instead to just do this and put out 2 tones, what we would hear would be 2 different specific beats. Now, What was annoying here was that it was only 8 hertz off, right? So if we could then strip out the annoying pitch, that 440 hertz, what we would hear is a tone of 8 hertz. We would just hear an 8 hertz tone, which would be very, very low. So let's instead say that it was 200 hertz. So if we combine something that was like 440 and 640, and we could strip out the 440 and 640 and just hear the difference, that would be the sound of this. That would be this. Not that. Although, yeah, that is that. But... So what we're basically hearing, we are hearing the combined sound that the basic frequency is being pulled away from it, and we are recovering it by mixing that center frequency that they've picked along with the center frequency that we're making. So that 8 hertz, woo, 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 if you were to raise that to the sound of somebody's voice, that's what you get back.
The voice?
Yeah.
Okay.
So in other words, if they, let's say that the transmitting frequency instead of 440 hertz was this frequency. 1 megahertz, right?
Mm-hmm.
And there was another signal that we had, which was 100 hertz. What's the difference right there? It's 1,000 hertz.
Mm-hmm.
If we could then add those and subtract them together, we subtract them from one from the other, we get 1,000 hertz. That's an audio frequency.
Yeah.
That's an audio frequency. And we can listen to that audio frequency and amplify it, and what we hear coming out of the speaker is a 1,000 hertz tone. That is demodulation. That is how we listen to things. We artificially introduce something, a frequency, that is close to the one that we want to actually listen to. So now, what if this were off by, let's say, a few hundred hertz? What would our tone be? Instead of 1,000 hertz, it would now be 400 hertz.
Mm.
And if that was a part of somebody's voice, their voice would be shifted, and they'd sound like, if we went the other way, they'd sound like Donald Duck.
Right.
Okay.
I have a question.
Yep.
I'm sorry, I should have asked it sooner, but you've been on a roll.
Mm-hmm.
Back up. How is a specific group of stations selected on a digital voice transceiver? And the answer is by entering the group's identification code.
Yep.
There's another answer there. It's by enabling the group's CTCSS tone.
Yeah.
Couldn't that also be a correct answer?
No, because CTCSS, okay, the way CTCSS works is that it's a continuous tone, and it doesn't work on digital radio.
Oh, okay.
That's specifically analog.
Okay. Thank you.
So yeah, CTCSS is a sub-audible tone. There are 38 of them. It's also known as PL, or private line. It was invented by Motorola to keep analog stations from interfering with other analog stations.
Hey, Scott, quick question.
Uh-huh.
Is there a difference between BFO with the B of big and BFO with the B of big?
And a VFO?
Yeah.
Well,
yeah.
I mean, a VFO is a variable frequency oscillator. A BFO is typically what we use to listen to. All right, okay. So if we were to draw a receiver, yes, they are different, because you basically you typically don't do what's known as direct conversion. You have information coming down into a mixer, and the mixer is mixed with a VFO frequency, and that goes into a filter. And because you have adjusted the VFO frequency, that is basically the tuning knob for the radio. Then this goes into another mixer, to which you have a BFO. And that's usually operating at a much lower frequency. And this goes into another filter, and then this goes through an amplifier into your speaker.
Now, a kind of roundabout question. You can do this, the repeater stuff with what? 2 meter, 4 meter? What else?
With regard to what?
Is there,
exactly?
I mean, frequencies that I mean, I know a little bit about HF, but nothing about, you know, UHF or so when it comes to these using repeaters and you gotta go to a club, I guess, and align yourself with a club. Or
no, I mean, you can just be anywhere and just, you know, the repeaters are typically made for the, you know, for the ham radio public, for anyone to use. So I mean, does that answer the question? Kind of.
I guess you got to look up what you said, the OR, your case it to ORC, look where the frequency is at, what frequency is, and then how do you plug yourself into that?
Well, you have to know how to read the you have to know how to read the, you know, kind of read the entries. I mean, here, this is the one I typically use. It's called Repeater Book. And this allows you to pick any location anywhere in the world and look up all the repeaters for that location.
Oh, okay.
So let's say we're going to Kansas. I'm going to look up all the 2 meter repeaters in Kansas.
Oh, I didn't know that. There's 10 meter repeaters too?
Yeah.
Wow.
There aren't many, but. So you pick where you are, you look and see what's available, you click on it, say, okay, let's take a look. And there's an iPhone app for this too. See, notice it's an open repeater. That means come and join us.
You mean a mobile app?
Yeah.
For us Android guys.
Right. There's an Android app too. But notice it gives a location, it gives the repeater call sign, it gives the outlet, you know, the frequencies with the offset, and it's an analog repeater, so it gives you a tone. Tells you how to get into it.
So if one, like, you know, me who's never had a 2 meter radio, just go out. What would you suggest? Go out, get yourself a 2 meter, a good 2 meter radio or something like that, and start using it like that way. Or
yeah. And of course, you know, hang out with your local club. Go find the
Right.
local club and get to know them. And
Speaking of 2 meter radios, and I don't mean to get into a long discussion, so a short, you know, comment would be fine. What are your thoughts about Baofeng?
we'll get to that. All right. Okay, station equipment. What's a transceiver? A device that combines a receiver and a transmitter. So we're on page 84. A portmanteau of transmitter and converter. A device that converts one band to another is called a transverter. Something that increases the transmitted output, that's an RF power amplifier. The function of a CWS or SSB CW FM switch of a VHF power amp, you will find that a lot of amplifiers have that. If you remember yesterday, we drew the picture of the power amplification curve of a transistor, and it looked like that. A CW and FM are not linear modes. They don't care what the signal looks like. They just want it to be at one particular frequency. Single sideband is a linear mode because it's amplifying voice. Distortion makes it sound bad. So that will change the mode of operation on that curve and it'll change the efficiency. Typically, single sideband is a less efficient amplifier because it has to be operated in the linear mode. And how do I get rid of that? Erase. There we go. Okay. Okay, what term describes the ability of a receiver to detect the presence of a signal? Okay, who here can whisper? Okay, whisper something.
Sensitivity.
Okay, could anybody not hear what was just said? What we're doing is testing out the sensitivity of everyone's ears. That's what a receiver's sensitivity does. Okay, now, on the count of 3, I want everybody to unmute themselves, right? This is going to be fun. Okay, on the count of 3, I want you to say your name. 1, 2, 3.
Joseph.
Okay, that is, if you could pick out a name in there, I heard a Joseph. That is called selectivity, the ability to discriminate between multiple signals. That's a receiver's ability to be selective. Okay, to improve the sensitivity of a receiver, you can use an RF preamplifier. You typically, if you have a satellite TV antenna, for instance, you'll typically have a receive preamplifier. It will be weatherproof and up at the antenna, because if it's down in your station, by the time the signal gets all the way down the cable, it's already weaker and you can't amplify what you can't hear. So an RF preamplifier is between the antenna and the receiver. Typically.
Hold it. You can't amplify what you can't hear.
Yep. All right. So I got to draw a picture. Okay. So we have an antenna.
What's the point of amplifying other than making something louder that you can't hear?
That's right. Okay. So let's say we have our receiver and we have our signal coming in, and our receiver has a sensitivity of minus 120 dB compared to a milliwatt, dBm. That's compared to a milliwatt. Our signal coming in is minus 115 dBm. So if we have no loss in this cable, will we be able to hear the signal? This is called the minimum discernible signal.
Yes.
Yes.
Sure.
Okay. What if we have cable that has minus 10 decibels of loss?
Oops.
Oops. What happens?
Can't hear it.
The signal down here is minus 125. What if we put a preamplifier right here?
No, it's still noise.
Yeah, it's still noise. If this has a sensitivity of minus 120 dBm, there's no signal to amplify. But what if we put an amplifier way up here, right up here at the antenna, which had a plus 10 dB gain and a minimum signal it could hear of minus 20 dBm? What would the signal coming out of it be? It'd be minus 105.
Mm-hmm.
Then we lose 10 and we're back at minus 115. Do we get our signal? Yes or no?
Yes.
Yep.
Yeah.
You can't amplify what you can't hear.
Could you remind us what the M is in dBm?
It means milliwatt.
Okay.
It's a reference to a milliwatt. That's why you can't amplify what you can't hear, and why it's important to amplify before the signal disappears.
It gets too noisy.
Yep. It basically disappears. There's no strength left, and all you get is noise. So you just make louder noise. Okay, a device used to convert one frequency to another is called a mixer. A circuit that generates a signal at a specific frequency is known as an oscillator, like a beat frequency oscillator or a variable frequency oscillator. And the act of combining speech or any other information with an RF carrier signal is modulation. There are lots of different ways to do modulation. There's frequency modulation, there's phase modulation, there's on-off modulation. That's Morse code. We just basically turn a signal on and off. There's frequency shift keying, where you have an oscillator and you just change the frequency by a little bit. You can have binary phase shift keying or frequency shift keying, which moves it from one to another. You can have quadrature, You can have 4 phase shift keying where you have 4 different tones, and you just basically move from one tone to another, and the receiver is coded to say, okay, I'm moving from one tone to another. This pattern represents a code. This other pattern represents a different code. Which of the following can cause radio frequency interference? Fundamental overload. All right, here we go. Harmonics are basically, everyone remembers harmonics. Harmonic is a multiple of a frequency. Spurious emissions are frequencies that are not harmonically related to a particular tone, a particular frequency. Fundamental overload. Okay, so what we're going to say, fundamental overload, is the inability of a receiver to reject noise, either in band or out of band. Okay, so what we're going
Scott,
to do.
I'm
yes.
sorry, I have a question.
Yep.
So the question before, we were talking about the channel shifting from, or frequencies up or down. Is that how it, I've heard trunk tracker scanners and things for various things. Is that similar to that or no?
That's frequency hopping. It's similar, yes. Basically,
Okay.
Except that basically means if it gets out of sync, it's going to completely lose the signal. So will this. So this would be 4 FSK, where you have like a 0, 1, a 2, and a 3. You can have 8 FSK, or 16 FSK, or 65 FSK, where you go all the way up to 65 or 64. And you basically, it looks like, in time, it looks like the player piano.
I got you. And then before it switches, it tones a certain whatever that other systems pick up on and know where channel it's going to.
Yep. Or you're basically programmed, if it's like, if it's a frequency hopping sequence, like trunked radio, basically, if it knows the sequence it's supposed to follow and it's time synchronized, it'll follow it. And if it's not, then it won't know where to go, and it'll just all sound like noise. So if it's got the right sequence, it'll hear it. And if it doesn't, then it's just noise.
Okay, I got you. Okay, thank you. I'm sorry to interrupt.
No. Okay, so where were we on that? We were on, okay.
Fundamental overload.
Fundamental overload. Okay, so let's say that we have a radio like this. And we have this antenna picking up frequencies from all over the place, all different frequencies, right? And we were to look at this on the frequency spectrum chart, and you would actually see frequencies all over the place, right? Okay, so let us say that this radio had no ability to discriminate between any of those. Basically, anything coming in is going to come into the first part of this radio. And the first part of this radio is going to be an RF amplifier. Right here. Where it's just basically, because these signals aren't all that big, it's going to just amplify whatever's coming in. So all the signals that are coming in are going to get amplified. Now, let's say that you happen to be, your intent is to listen to this tiny range, but you don't have any selectivity in your amplifier. Your amplifier only has a certain amount of oomph behind it, right? It can only do so much. And there's a bunch of signals that are like really big way over here. Do you care about those signals? Yes or no? We already said that the ones you really want to listen to are right in here, right? Do you care about those other ones?
If you're hearing everything, yeah.
Yeah, you really care about it. You don't really care what's there because it's not what you're interested in listening to. But that amplifier is wasting an awful lot of its energy doing what?
Listening to it.
Listening to those signals. It's amplifying it whether you want to or not. So
you're not going to hear your signal.
That's right. So what would be something that you would build and place in front of the amplifier in order to make sure that that doesn't happen?
A filter.
A filter.
Yes.
And you would build a filter that goes like this, so that it pre-blocks those signals that you don't want to listen to, so that by the time you actually use your amplifier, these signals are not there. Okay, so this brings up the Baofeng. So if I were to go to, let's say, a Yaesu handheld, which is this radio, which I love this radio. This radio is about $150 to $200. I also have a Baofeng, which is about $25. They both will receive a weak signal very, very well. What is the fundamental difference between this radio at $150 and this radio at $25?
Price.
What do you think? Besides
The
price,
filter.
the
No
filtering,
Quality.
the filtering, the filtering is the fundamental difference. This radio, when you tune it, has some really good filtering ahead of the amplifier, and this has very, very little. So if you're operating in a very quiet environment where there's not a lot of other RF floating around, the Baofeng will do just fine. But if you hook it up to a bigger antenna, it has what I call a glass jaw. You punch it in the face and it just falls to the ground. If there's other stuff floating around in the environment, it becomes deaf. That is the fundamental difference.
I imagine filtering, analog filtering in such a tiny device has got to be tricky.
Mm-hmm. I mean, but you certainly do it. I mean, we do it in our cell phones. Our cell phones have lots of filtering.
That's true.
So
But they're digital.
What was
no,
that
it's
type
not.
again that you like?
There's analog filtering in there first. I mean, there's some digital filtering, but there's analog filtering first.
Scott, what was that good radio? I mean, you're talking about two radios, and
Well,
the more
in my case, it's a Yaesu, but it could be any. I mean, basically, if you're looking at a $25 radio versus any $100-something radio, that is the fundamental difference.
okay.
And that is the filtering. How good the
Filtering,
RF,
yes.
how good the RF section really is.
But you had that Baofeng sitting right there. So do you
I
use
do.
it very often?
I don't use it that often, but I do have several of them.
Mhm.
They're great for certain things, like if you don't care if it falls into the water and you never see it again.
Oh,
For
God.
$25, you're really not out that much. Right? Or you accidentally drive over it with your car. Or you loan it to somebody who's never been on the air before.
What about, and again, without going down a rabbit hole, but what about the legal controversies surrounding it?
I mean, are we talking RF signal purity, or the fact that it can be used to operate on many, many different bands? I've owned 6 of them. I've never used mine illegally, to my
Right.
knowledge.
Yep.
I mean,
Okay.
lots of people do, but that's really on them. So, that just indicates that they don't really know the legality. So,
But
Okay,
Scott,
yes.
isn't the difference between a Yaesu and a bed, whatever the heck that is,
Baofeng.
the difference between a Mercedes and a Kia?
No, it's more like the difference between a Mercedes and a Lada.
Wow.
Wow.
Or a Yugo.
Oh, no, a Yugo is still better than a Lada.
Wow.
So, or yeah. I forget what was the East German car? A Trabant.
Oh yeah.
Yeah, it's kind of between a Mercedes and a Trabant.
But for $25, it's affordable to play with.
Right, exactly. You're not gonna, and I've killed several of them, not really doing anything. I've killed a few of them. I don't know what I did, but I don't really care. Okay. Which of the following actions would you take if your neighbor tells you that your station's transmissions are interfering with their radio or TV? Well, that sounds like a problem with fundamental overload, doesn't it? It could also be that you're transmitting on one of those frequencies with spurious emissions or harmonics. So the first thing to do is turn on your own TV and make sure that it's not interfering with your TV. Well, if it's not interfering with your TV, maybe it's not your problem, but maybe it is still a problem with their TV.
Is this still a problem with cable and
Oh, yeah.
streaming?
Oh, yeah.
Really?
Oh, yeah. We're getting to that, too. What should be the first step to resolve non-fiber optic cable TV interference caused by your transmissions? There are still cables. Well, the biggest thing is that those little F connectors on cable TV unscrew slightly. When they unscrew, the system is no longer sealed, and it leaks, and it also allows leakage in. And cable TV operates on a very, very wide range of frequencies, including ham radio for that matter, from one end to the other of the spectrum, because it's a sealed system. It's a closed system. But if it's suddenly not closed, if it's leaking, if it leaks out, it can also leak in. What would cause a broadcast AM or FM radio to receive an amateur radio transmission unintentionally? Signal rejection. The receiver is unable to receive strong signals outside the AM or FM band. Most car radios, for instance, are not really designed to be, $500 radios with a lot of filtering. Similarly, let's say that you are driving past an AM transmitting station and it doesn't matter what frequency you're tuned to. You hear it anyway.
Yeah.
That is the same kind of deal. It's maybe your problem. It's maybe their problem. The solution is really that everybody's operating legally. You could install a filter, but the easiest way to do it is just drive away. Which of the following can reduce overload of a VHF transceiver by a nearby commercial FM station? You can install a band reject filter. That basically is a notch filter to notch out ahead of your receiver the signal that's the offending signal. Something in your neighbor's home is causing harmful interference to your station. Okay, so there is a part of the FCC rules called Part 97 that governs the amateur radio service. There is also something called Part 15. If you take a look at your computer, your power supply, your lighting, everything is Part 15. Part 15 covers unintentional radiators. And that basically says that anything that's electronic is allowed to radiate unless it causes harmful interference to a licensed service. Well, we're ham radio operators. We have licenses. We are a licensed service. So if somebody is using an LED light, we actually have problems here with grow lights in Eugene, believe it or not, for people with pot grows. They use cheap Chinese-made lamps, which put out a lot of RF.
Especially in Eugene.
Especially in Eugene, that's right. And the FCC has actually been cracking down, not on them, but on the manufacturers of noisy lamps out of China.
So Scott, here, this is a question I've had for a long time, that Part 15 thing. So I grabbed a random piece of electronics here in my office house, and sure enough, it has this statement on the back of it.
Yep.
And the one that I'm wondering that makes no sense at all to me is this device must accept any interference received, including interference that may cause undesired operation.
Correct.
What is that telling me?
That tells you that it's an unintentional radiator, and it also has no rights. In other words, if I have a legally operating transmitter and when I transmit, it makes my garage door open, it's the garage door opener's fault. It's the garage door's fault. That's what it means. It means that they're electronics, and the legally operating station is not responsible for fixing your problem.
That makes more sense.
Even though it's them.
Even though it's them. Well, they're operating legally.
Yeah.
They have a license and are operating legally. Does that mean you shouldn't help your neighbor? No, it doesn't.
Yeah.
But you're not obligated to.
Well, a lot of this gets back down to filtering, right? So
Filtering,
the company that made this device doesn't want to spend the money to put an expensive filter in there to keep it from, shutting down.
That's exactly right. For the 1 in 1,000 cases when it's actually a problem.
Now, one other comment about filters, since we were talking about that. I mean, I get that and it makes sense, but there's always a downside, right? So putting a filter in line with your system
money
increases loss, right?
A little bit.
So, but that's where the money is.
Money. Yep.
Yeah. If you want to minimize the loss or the insertion loss, then you got to spend more money.
Yep. It's always about money. And nobody who makes a commercially made something wants to spend money on something that's only going to be a problem 1 in 1,000 times.
Yeah.
Okay, what might be a problem if you receive a report that your audio signal through a repeater is distorted or unintelligible? Well, if you're off frequency, that'll definitely do it. If your batteries are low or you're in a bad spot. If you're in a bad spot, that means your signal is just weak. So it ends up sounding distorted or full of noise. FM is really not a good weak signal mode. FM is best when the signal is good and strong. RF feedback causes, again, garbled, distorted, or unintelligible voice transmissions. That's basically where you have RF being transmitted and it's being picked up by your microphone cable. So, how would you knock that out if it's being picked up by your microphone cable? What do you think you'd put on your microphone cable? It starts with the letter F.
Ferrite.
A ferrite choke. Yep. So on my computer, I have a USB cable and I have a couple of other cables that are connected between my computer and my radio, and another one going to the microphone. And what I found was that if I transmitted at a certain power level, it would actually cause my computer to lock up and force me to reboot. So I have 5 ferrite chokes on my USB cable. The reason I have 5 ferrite chokes is that I still had a problem when I had 4. So I added a 5th one and the problem went away.
Did you space them out along the cable?
I did.
So you're trying to interrupt the wavelengths of the signals that are getting on there.
It doesn't really matter where you put them so much. I just, I didn't want to put them all right next to each other. So I spaced them out as much as I could.
And that is one thing that's cheap.
Yeah, ferrites are relatively cheap. And what can you do if you're so if you're using a bigger radio, it'll typically have a microphone gain control. Well, we don't have a microphone gain control on a handheld radio. The microphone gain control is that I'm going from talking way up close to the mic to moving it 6 inches away. So that's how you change the mic gain.
Scott, real quick, what's over deviating?
Over deviating. Okay. Well, all right. So FM is different from sideband. So the way that FM works is that you have a center frequency that looks like that. And when you speak into your microphone, it causes the signal to basically fill in a space. The louder you are, the higher the frequencies are, the more the signal spreads out. And most FM radios on what we use have a nominal bandwidth of plus or minus 5 kilohertz, where they will spread out. And because of that, most receivers are listening for plus or minus 5 kilohertz. So they take up a total bandwidth of about 10 kilohertz, which is why most people there's very little FM on the high frequency bands, because there's not that much room to put stuff. There's not that much bandwidth. If you are speaking too loudly, or your radio or your FM transmitter is over deviating, there's a deviation factor built into it, your signal might actually come out to, let's say, plus or minus 7 kilohertz. And what happens to that stuff that's outside of 5 when it gets to the receiver? The receiver's only listening to this in the filter. So what happens to all that other stuff? What is all that other stuff? What does it represent?
Noise.
No, it's part of your voice. So if you're putting if you're putting out signals wider than the receiver is listening to them, part of your voice, part of the information that is indicating that it's you talking, is now stripped out. So obviously you're going to start to sound distorted. So if you're over deviating, that's a result.
Thank you.
Okay. Measurement of voltage and resistance and stuff. Okay, so a multimeter typically is going to measure voltage and resistance. To measure electric potential is measured in volts. The meter would be called a voltmeter. How do you measure voltage? If I draw a something or other that looks like this. Here's my battery. I want to see what the voltage is. I would go from here to here, and I would put a voltmeter right here, measure it across, and it measures the electric potential between 2 points. Now, so that is in parallel with it. And let me get rid of that. Okay, so now moving on. How would you measure? Let's see, another thing to measure is resistance. Okay, so everybody, real quick, what is Ohm's law? Somebody?
E equals IR.
E equals I times R. Okay, so what we're going to do is we're going to draw a resistor. Here's our resistor. So if we have a voltmeter, well, how would we measure resistance? If E is equal to I times R, and we can draw our circle, EIR, we cross that one out. R is equal to E divided by
E
I.
divided by.
That's right, E divided by I. Okay, well, how do we make an E and an I in this circuit?
Measure your voltage with a voltmeter to get the E.
Right, but what voltage? There's no voltage. So what we do is we go like this, and we have a battery, and then we have an ammeter that goes like this. We have our battery voltage. This is actually a battery that's built into our voltmeter.
Yeah.
And we do this with it. It generates a current that flows, and it comes through our series ammeter. Our ammeter is in series. So if we know our volts and we know our amps, what do we know?
What does an ammeter measure?
Well, what do you think?
The current?
Yep, ammeter measures amps, which measures current. So if we know our voltage, because we provided the battery, it's a test battery, and we know our current because we just measured it, then we know our resistance. So this is really important, because what if we had another battery that was already in the circuit? We would get some very unpredictable results.
Yeah.
So before measuring a resistor, you have to disconnect it from the rest of the circuit. So now what I'm going to do is, let's say that we actually have a mystery thing that looks like this internally. What is that right there?
Capacitor.
That's a capacitor. So what happens if we have a battery that charges up a capacitor? At first, the capacitor is empty, but then what happens once the battery charges up the capacitor?
Has a little bit of voltage.
It's full. That's right. And once it's full, how much more current can you stuff into it?
Zero.
Zero. Yeah. So if we have a resistance meter, and we see that at first the resistance is 0, and it goes like this, and it goes up to infinity. I'll draw that right. Let's draw that better. That means that we have a capacitor in the circuit that we're charging up. Because otherwise a resistor would just, we'd see a value and it would stay constant. So this is what a resistor looks like when being tested. And this is what a capacitor would look like when being tested. So that's how you can tell if you have a capacitor in your circuit. Okay. All right, which of the following can damage a multimeter if you try to measure voltage when using the resistance setting? Because it has a battery thrown in, you might blow something up in your meter. Which of the following precautions should be taken when measuring high voltages? Okay, so has anyone ever been to Harbor Freight?
I'll admit it.
You can admit it. I've been there too.
Yep.
Okay, sure. Harbor Freight. Harbor Freight has its wonderful place, right? So you can go to Harbor Freight. Oh, look, giant liquidation. We can get a multimeter. We can get a Harbor Freight multimeter. And
I think
let's
you got to
see.
switch screens, Scott.
Yeah, here we go. I just had to pull the right thing up. Let's here we go. Harbor Freight. Okay. $6.99. And notice that it says it can measure up to 250 volts DC, 250 volts AC. And now I can also go to just about anywhere and buy a Fluke 87.5, 87V. All right. So how much is this Fluke multimeter?
A lot.
And as this loads up, this Fluke 87 is $450 to $500. And this can be this will go up to 600 volts. So which one would you trust more? Would you trust the Harbor Freight meter or would you trust this one?
Luke,
To measure high voltages.
oh, high voltages.
Yes. Or just for accuracy. You know, at 24 volts, you know, at 12 volts, even at 120 volts, it's probably okay. But I have to think that this one, which I have, and I throw it in my tool bag to measure DC voltages, would probably be just fine for low voltages. If I'm risking my life at work because I'm measuring 480 volts and I'm all suited up, I'm going to use my Fluke.
Yeah.
And that is the fundamental difference, that the leads on the meter are really designed for high voltage. The meter's probably not going to blow up.
Okay.
So make sure that your voltmeter and leads are truly rated for the use at the voltage is being measured. That's a safety thing.
So I've got a question about meters.
Yep.
You know, you can get a cheap meter like that, or you can get a meter that is advertised as true RMS.
Yeah.
And
there's a difference.
I have a Fluke meter, which is true RMS. But I keep wondering, what if I wanted to measure peak voltage and not RMS voltage?
That is a good question. And I honestly don't know. The thing is that even a standard meter is going to do its best to measure RMS.
Right.
It's not going to read peak measurements. Peak measurements, there may be a peak function on some of the meters, but I don't know.
I mean, I could always do the math and figure it out, right?
Well, if you know what the waveform looks like, yeah.
True.
You have to know what the waveform looks like. On a square wave, the peak voltage is the same as the RMS voltage.
Kind of.
No, it is on a square wave.
But that's not the same. Is that still the same as the average voltage?
Yeah. In a square wave, yes. Triangle wave, sine wave, sawtooth, they're all different.
But if you have a square wave with a 50% duty cycle, it's full voltage and then it's half voltage or no voltage.
That's different. I'm talking about a continuous square wave. If you have a 50% duty cycle, then that changes. But the RMS of a continuous square wave is the same as its peak voltage. You can do the math. The square root of the integral of, or what is it? Yeah, square root of the integral of v squared t dt. It's basically time average divided by the time.
Also flipping all the negative to the positive, and it just turns into DC.
Right. Okay, when measuring, how is an ohm meter connected for a component to measure its resistance? It's in parallel. When you're measuring a resistance in a circuit, you need to make sure the circuit is not powered. Very often, it's very important to even remove one of the leads from the circuit board to make sure that it's not connected to anything else. If you see a resistance that changes with time when you're doing the measurement, that means you probably have a big capacitor in there. To measure electric current, that's an ammeter. The tricky thing is that an ammeter, if it's a true ammeter, is going to be in series with the circuit. If it's in series with the circuit, that means you actually have to insert it, which means you might have to cut something and insert it. Unless, of course, because we know that every current that's flowing makes a magnetic field. If you can use something that measures the magnetic field, which is known as a clamp-on ammeter. It has a little ferrite in it, and it creates a magnetic field, which you can then use the magnetic field to generate a current and a voltage. You can actually measure that indirectly. There are two kinds of solder, acid core and rosin core. We typically use rosin core. Acid core is bad for circuit boards. Rosin is the same stuff that we use to on horsehair bows for violins. A cold tin lead solder joint is going to look lumpy. A nice solder joint is going to be smooth and shiny, and when it's that means that everything's gotten hot enough for the solder to totally melt and connect to everything.
Hey,
All right.
Scott, question,
Yes.
please.
Yep.
I was confused about your answer on the previous one about the solder type, the acid core and such. I thought you were offering an answer that was different.
Acid core is for plumbing.
Okay, I thought you were offering an answer that was different than the one that was described in the printout.
Nope, we use rosin core. Oh yeah, well we use rosin core. We never use acid core.
Oh, it's not to be used. I didn't
Yes.
see the not. Okay, understood.
Yeah, we use
Thank
rosin core for soldering. Never acid core. Okay, we're on to operating procedures, FM operation. Okay, the thing that puts out a signal that it receives, puts out a copy of it, is known as a repeater. Stations that are permitted to automatically, now this automatic retransmission is really important. There are only 3 things that are allowed to automatically retransmit. They're a repeater, an auxiliary, or a space station. A repeater is basically on a mountaintop, I send a signal out, it resends it. A space station is anything 50 kilometers up or higher. So that can be something that's automated. It could be a repeater on a satellite. It could be a repeater on a really high altitude balloon. An auxiliary station is like a forwarding machine where, let's say you have a whole bunch of different repeaters that are on different mountaintops, and it's not necessarily a repeater, but it could be, let's say, a forwarding station that is linking one repeater to another. It's not really intended for people to be listening to it, like a microwave signal. And it's designed to connect one station to another. That's an auxiliary station. A linked repeater network is a network of repeaters in which signals received by one repeater are transmitted by all of them in the network. We have one in Oregon that links together 50-something repeaters covering the entire state, and then down into California, over into Idaho, Nevada, and up into Washington. And they're all linked together. So if you have a handheld radio, you can get into one, you get into all of them. You can have conversations over hundreds of miles just from a handheld radio, which is very, very helpful in case you get into emergencies. When we had fires last summer, that became a very, very active place for people to be. The most common repeater offset in the 2-meter band is plus or minus 600 kilohertz. The break point is right around 147.000. So if you're above 147, it's a positive offset, and if you're below 147, it's a negative offset. In the 70 centimeter band, the repeater offset is plus or minus 5 kilohertz. And that's going to be specified again in the repeater guide.
Correction.
Yep.
5 megahertz.
Sorry, what did I say?
Kilohertz.
Oh, 5 megahertz. Yeah, plus or minus 5 megahertz. Thank you. Subaudible tone. Subaudible tone is a very low frequency tone that is transmitted at the same time as your voice. It's also known as CTCSS, that a receiver, like a repeater, will listen to. If it hears it, it will accept your signal. If it's not there, it will not. There's another type of squelch. CTCSS stands for Continuous Tone Carrier Squelch System. DCS is Digital Code Squelch. It's actually a very rapid frequency hopping system that changes your transmitted frequency just a little bit at a time. The receiver is listening for it, If the receiver doesn't pick it up, it will reject you. So if a repeater can't hear, if you're not getting heard by a repeater, you could have the wrong offset, you could have the wrong tone in, or you could have the wrong DCS code. Reverse on your handheld radio. Every handheld radio has a reverse function that allows you to, instead of listening to a repeater's output, allows you to listen to a repeater's input. The reason for doing that is, let's say there's somebody nearby who is having issues getting into the repeater. You might be able to hear them transmitting if you live close to them. If you're transmitting too loudly, you're talking too loudly into the microphone, that would cause over deviation, which could cause you to become distorted. How do you call somebody over a repeater? Kilo Lima 5 Tango. This is N7JI. Over, Kent. You there?
Roger. N7. This is what we missed your call. N7JI scale 5T. Go ahead, Scott.
All right. Thanks, Kent. And, I was going to say that this was N7JI monitoring, which is the next question, except for the fact that I noticed that KL5T I thought was there this morning. And so with that, I'm going to pass it over to you so you can say hi to everybody. And we're cruising right along. And go ahead and take it over, Kent. N7JI. Over.
Good morning, Scott. Thanks for putting on the class again. You've helped a lot of people become hams. So good work. But I'm the chairman of the Anchorage ARC BEC. And of course, many of you are going to be testing with us today. And I just thought I'd stop in to see if there were any questions about that process. And I don't want to take too much of Scott's time, but if anybody has any questions, hit me here on voice. I'll take your question, or you can chat me. I'll stick around for a few minutes. Okay,
can you just verify the time zone time?
Yeah, the time is listed at Pacific time.
12:30 Pacific.
But so there's 21 of you. We've got a team of VEs ready to go. So we need you to just basically we're going to call you when it's time for you to join the Zoom call. Okay. So we don't have a big mass of people and just sitting there. So if anybody needs to test early, let me know. You can chat me here, and we'll make sure that we get you done, because you might have some other things you need to take care of. And let me see, Eric Wolf.
Hey, Kent, just so you know, you're a little distorted.
Yeah, I'm sorry. I was looking for the call-in phone number for this because my network connection is not great. So I was going to try to call it on my phone.
Actually, it sounds better when you get closer. It might be an audio thing.
Okay, we'll do that. Yeah, and I'll see. I do have to be done by 1 p.m. Somebody said that it's Christian, I think. What's your time zone? Is that you in West Coast time?
I'm West Coast. I'm a caretaker and something came up.
Okay, so we'll make sure we get you on the top of the list, okay?
I'm in Chugi. And that's Christopher First, right?
Yeah,
that was.
I've got a chat message.
Okay.
Yeah, Christopher Shaglick.
Slogheck.
Yeah.
Slogheck. Got it. Okay, very good. We'll make sure that happens. Anybody else?
Or if you need to go really late for whatever reason, that's another thing. If you want to be like last.
You want to do some more cramming.
I think Terrence raised his hand.
Yeah, I'm out in Chugiak.
Okay. All right, I'll tell you what, it's a little bit confusing for me here. So just hit me on chat, and I'll answer each of you individually, okay?
Sure.
Okay.
All right, cool. Thanks, Kent.
All right, thanks, Scott. I'll get out of here and I'll tend to folks here on chat. So
all right, KL5T.
Quick question.
Kent. Oh, wait, there's another question. Go ahead.
Sorry about that. Yeah, Ken, not related to the test, but for the Anchorage Club, all the stuff that we've learned over the past 2 days would really help me a lot if I was able to see some of the stuff in person and how it operates. So how often do you guys get together in person there?
Right, so we're down there every Wednesday morning for sure, doing shares from 7 till at least 11. We're also there on Wednesday evenings to run the South Central Simplex Net. We're there from about 5:30 till 9. And then we're always there on Saturday mornings for working Saturdays. And then we're there at other times for various things. But those are kind of the scheduled things these days. And you're always welcome to come down when we're there. We're happy to show you this stuff. And being there for shares or the South Central Simplex Net, those are great training opportunities, both on VHF, UHF, and on HF. Some serious HF work going on there.
Awesome. And then what time is that on Saturday mornings?
Usually by 9 o'clock, yeah.
And Kent, where are you? I'm in Anchorage too.
Yeah, well, you mean where's the club located?
Correct.
The RSOC, the Radio Science and Operations Center. It's located at 6721 Raspberry Road, down there on the way up to Kincaid Park.
Got it.
It's in the former FCC monitoring station. If we're there, you'll see cars there. When you pull up, the gate will be closed because we have to keep the moose out.
Correct.
Alaska problems.
Yeah, we got to keep the moose love to run that corridor on the roadway, and they dive in, and we've got antennas and tables and all kinds of stuff, and we don't want to get tangled up. Okay, so just call the number on the gate, and we'll open the gate for you and let you in.
Roger that. Thank you.
Appreciate it.
All right, cool. Shall we continue on? Wait.
All right, I'll hit the chats.
Okay. Wait. We got a hand up from iPad.
How many times can you test?
You mean like how many times can you try, like today?
No, like if you don't pass, say you don't pass the first time, are you allowed to test again?
Yes. So if, like, for instance, if you absolutely. So let's say you fail miserably and you're clearly not ready to test. That would suggest you need to do some more studying and then come back at anytime you think you're ready, you can test again. Okay. You'll have to, if you come back at a different session, then you'd have to do the whole process. Now, if you test today and you're close, you're within a couple of questions of almost passing, we'll likely give you another shot today. Okay. Because remember, we're on your team. We want you to pass. Okay. So we're rooting for you. Okay.
Yep.
All
right, cool. Thanks, Kent. You're going to stick around for a little bit, huh?
I'm going to hit the chats here.
Okay. All right. Thanks, all. All right. Let's get back to this. And, okay, so we are looking at this. Why are simplex channels designated in the VHF, UHF band plans? The reason being that if you're only a mile from somebody and you just want to have a conversation with somebody, there is no reason why, there's nothing saying I have to talk with everybody. You know, if I just want to have a talk with my wife, for instance, or my daughter, and we're only a half a mile apart, there's no reason why we have to tie up an entire repeater. A repeater is a resource. There's also no reason why other people, we have to it's not a private conversation because you're not allowed to do that. But, if you're only, let's say I'm upstairs and my wife is downstairs and we both grab a radio and we're operating at 10 milliwatts, nobody else is probably going to hear us, but it's still legal. So that's why there is such a thing as simplex. And the national simplex calling frequency is 146.52 megahertz. You're going to want to commit that to memory because virtually everybody, there's virtually somebody everywhere monitoring that frequency, even if you don't know the repeaters. Okay, now we're on to HF. We are on page 97. CQ means calling any station. I'm calling CQ. This is something that we would do on HF. You don't usually do it through a repeater because a repeater, you just basically say N7JI listening because there's another device that you expect to be there. But if you're just calling on an open frequency, you would say CQ. This is N7JI listening. Now, before calling CQ, because on the high frequency bands, we sometimes have weird propagation things where people can't necessarily hear each other, even if they're only a couple of miles apart. And this comes back to that geometry that we drew yesterday, where you're aiming stuff at the sky. You can aim signals so high that they go right through the atmosphere and up into space. Sometimes you are only able to communicate with people 1,000 miles away, which means that if I have somebody who lives in Portland, we might both be able to talk to the person on the East Coast, but we can't hear each other. So if I start listening and I say, I don't hear anything, well, the first thing I'm going to do is, okay, well, I verified I don't hear anything. So that frequency might be available. The next thing I'm going to ask is there anybody using this frequency? Is the frequency in use? I would not hear the Portland person talking to me, but the Portland person might be talking, and the guy on the East Coast might actually be talking to them. At which point they'll say, "Oh, hey, yeah, the frequency is in use." Even though I couldn't hear anybody talking, the frequency is in use. So the first thing you do is you listen. The second thing you do is make sure that you're allowed to be transmitting there in the first place, because depending on the license you hold, you may not have privileges there. That's why it's really important to understand the band plans and who's allowed to be where based on your license. And then you would call CQ. If you ask, first you ask, is the frequency in use? And if there's nobody there, then you can go ahead and call CQ. If somebody calls CQ and you're the station responding, you would basically say, let's say Kent is calling CQ, 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 Kilo Lima 5 Tango, and I'm N7JI. I would say KL5T, this is. So indicating, hey, I'm calling you and here's who I am. Other stations call and then you're on call. So if Mac is calling, hey, this is Mac calling CQ. Is anyone around? I'd say, hey, Mac, this is Scott. Right? You always address the other person first. When making on-air test transmissions, there's a rule that says that every transmission that you make on the air has to be identified every 10 minutes and at the end of transmissions, at the end of communications. If you're making an on-air test transmission, you don't know if that's going to be the last one, so the easiest way to make it legal is to say your call sign. By identifying your signal with your call sign, that makes it legal. Now, you're also allowed to operate on Morse code. There are 2 Morse code signals that you will use frequently. There's actually a whole bunch more, but the ones that they ask in particular are QRM, which is man-made noise. That means interference. I'm getting QRM. The other one is QSY. QSY means I'm changing frequency. And frequently you'll actually hear people use these signals on voice as well, even though they're specifically Morse code things. For instance, if you're changing to a different repeater, you're going to say, you'll hear people say, I'm going to QSY to the Valley Club repeater. I'm going to QSY over to 14545. Hey, I'm getting QRM here. Let's go to a different place. Okay, a band plan. We looked at ORRC. We also looked at the band plans that are published. You know, that other chart that looks like this. All the FCC really says, with a very few exceptions, like these little red zones down here, is thou shalt transmit completely inside the band. That is another way that ham radio is different from virtually any other service. Most services, every frequency that they have is channelized. Channel 2, Channel 4, Channel 18, Channel 6. They relate to a certain center frequency and a certain bandwidth that's allowed. There is nobody saying, for instance, when we were tuning around on that SDR, that somebody had to be exactly on 14225.0000000. You could be anywhere, so long as your whole signal is within the band. So a band plan is a guideline that allows us to basically coexist with each other. So our band plan says that if you have a particular license class, this is the mode that is going to be permissible. You're going to have at 24.930 and above, you're going to have voice. 24.890 to 24.930, for instance, you're going to have Morse code and teletype and data. and that is to basically keep the peace. It's to have mode specific areas, and it's a voluntary guideline with a very few exceptions. And again, it's designed to keep the peace. Nobody owns a frequency unless there's like, you know, an emergency that's been declared, like there's a frequency that's specifically set aside for use in a hurricane, for hurricane response or for earthquake response. Nobody owns a frequency. Even if they've been there every single day at the exact same time on the exact same frequency for the last 40 years, nobody owns a frequency. They may think they do, they don't. So that means that basically whoever's there first is on the frequency. And if they say, hey, you know, we're about to run a net, maybe it's good courtesy to say, oh, okay, I'm going to move up. And then you would say to the person you're talking to, hey, let's QSY up 5 kilohertz. There's that QSY.
Scott,
Yes.
I have a question. Is it the same frequency when it's a hurricane every time? And is a hurricane frequency different from an earthquake or a tidal wave?
No, not really. I mean, it's usually going to be like 7268. That's going to be a frequency that is frequently used by, you know, coordinated by the ARRL and FEMA, for instance. Go ahead, Kent.
I was just going to mention there's the minor exception to that, I guess, would be relative to coordinated repeaters.
Right. Right. But again, I mean, there's nothing saying you can't be on a particular frequency, even if it does, you know, interfere with a repeater, although you're not supposed to interfere with other stations.
Got it. Thanks.
Okay, so if that's the case, you negotiate with the other station and you move accordingly. So, okay, now we are on to public service and emergency communications, which is obviously of some interest to some of you folks who are here. ARES, which is the Amateur Radio Emergency Service, and RACES are very similar. The one difference that you'll see, ARES and RACES, the C has civil. So if it's civil, that basically means that it somehow involves the government, civil defense. So ARES is a volunteer service for providing emergency communications. RACES is a volunteer service for providing emergency communications that is specifically in respect to civil defense communications. They're both volunteer organizations. With RACES, because it's kind of like a governmental thing, because it's civil defense, instead of just registering with ARES, which is run typically by the ARRL, you'll typically you'll typically register with your local civil defense agency. You can certainly operate with both. There's nothing saying you can't do both. Net control, if we're running a net is short for a network. It's a system that allows people, like Kent was mentioning, they run nets, we run nets. There are nets everywhere. A net is an opportunity for people to practice talking in kind of a controlled, somewhat more rigid environment than just having a general conversation between two people. So net control is sort of like the hub of the entire network. The net control station typically is responsible for controlling the traffic flow. Traffic is information, people talking, for instance, from point to point across the network. The net control station might also be responsible for passing traffic, which is information from between two stations that can't hear each other mutually. So net control station is basically, the job of the net control station is to run the net and direct the communications. And Kent's got his hand up.
Sorry, I never lowered it, or that was an accident.
Oh, that was an accident. Okay. All right.
Hey, Scott?
Yeah.
I have a quick question and curiosity. So the nets, and no one owns the frequency.
Right.
It happens. I mean, just for people that aren't familiar with it. For example, being a slow learner, I have a boat. And every morning at 8 o'clock, there is some net I am on the UHF net, but and I often control the marine frequencies, but there are also others, SSB and ham. I mean, and it's just automatic. You tune into a certain place at 8 o'clock Mountain Time. So what you're saying is anybody could just be on that frequency were it not for the courtesy they extend to the net and say, "Oh, sorry, you guys got to go somewhere else."
Yep.
Wow.
Yep. Well, I mean, you know, nobody owns a frequency.
That's wild.
It works both ways. You know, typically, you know, if we're going to run a net, we'll say, hey, you know, we're going to start a net in 5 minutes. And if there's somebody there, you know, if they're doing something that's really important, we'll wait. And if they're not, and they say, yeah, we'll move, they just move. Because, you know, nobody really wants to create friction. There are some people who do. But
I've never heard that happen. I've never heard, I've never heard somebody say, nope, sorry, we're already here. So that's just new to me.
Yeah, it happens. Some people are like that, but it's not that common. And now Kent really does have his hand up.
I do. So you're very right about that. Sometimes there may be an activity going on the frequency where a net typically meets at a certain time. I've been on plenty of nets where we've moved the net to an alternate frequency. We've shifted off a few KCs one direction to the other. And the beautiful thing about amateur radio is we can tune the dial. It's pretty easy for us to move and do these sorts of things.
Anna?
So are JD and Kent the ones that are doing the test, or like, or are
There's a
you
whole
gonna
bunch of
be-
us. There's a whole bunch of us. You're going to meet a lot of people. Okay, let's see. Which of the following is a standard practice when you participate in a net? Unless you're reporting an emergency, you'd either say emergency or break or throw out your call sign. To keep the net quiet, you're only going to transmit when you're asked to. Traffic is messages exchanged by net stations. Good traffic handling. This is where something called the phonetic alphabet. There are lots of different phonetic alphabets. We use the ITU phonetic alphabet, which is the International Phonetic Alphabet. Alpha, Bravo, Charlie, Delta, Echo, Foxtrot, Golf, Hotel, and so on and so on. The more you operate, the better you will be at it. This is why we use it, because our job as traffic handlers is to be accurate, right? We have let's say that Anna, like yesterday, I misspelled Anna's name because I thought it was Anna. So I spelled it Alpha, November, November, Alpha, and she corrected me to Alpha, November, Alpha, which is Anna. Now, if she didn't do that, let's say we were, you know, I was passing information and she's, you know, somebody said Anna. There are two different ways to spell it. They might be two different people. You know, if we're reporting an injury or something, we don't want to raise the alarm that somebody is really somebody else. So in that case, you would actually want to spell it. So passing information accurately is very important.
Scott, question, is the international alphabet the same as the NATO alphabet?
I believe it is. Kent?
Yes,
Kent
it is.
says yes. Okay, there we go.
Okay. Very good.
Okay. The preamble of a formal traffic message is information needed to track the message. The check in a radiogram header, radiogram is basically traffic. It's a formal message format. And it's the number of words or word equivalents. So if you count, I am going to the zoo. 1, 2, 3, 4, 5, 6. If I said, I am going to the zoo, and your check is 7, there's a word that got lost in there. It said, wait, the check doesn't match. I need you to repeat the whole message. So that's what the check is for. When do the FCC rules not apply? And the answer is never. If you're a licensed station, the FCC rules apply. And even if you're not a licensed station, the FCC rules still apply. So are you ever allowed to transmit outside of the privileges of your license class? And the answer is yes, but there are only two things, and this is going to show up all the time. Immediate safety of human life or protection of property. The dam is about to break. there's a fire that's about to burn my house. Somebody just had a heart attack and there's no other way to get help. Those are, you can use any means that you have at your disposal to get help. Now, there was just a case a couple of years ago where somebody went on, I believe it was like a wildfire frequency, and was trying to direct the wildfire forest fighters, the wildfire forest firefighters to
Say
the
that fast.
location. Yeah, say that 10 times. Try to direct them to the location of the fires. And his cell phone would have still worked. He could have still called somebody. He could have still gotten on the radio, but he grabbed the fire frequency and popped on. And I believe his fine was $38,000. So, if you do something where you go outside of your privileges to operate, you better be damn sure that there's no other way to do it, because you're going to have to justify it later. Okay, amateur satellite operation. Which amateurs may contact the ISS? Well, that would be, including me, anyone with a technician class license or higher can do that. Now, the reason that says technician class or higher is because there are still people who have a novice license. Novice license does not give you access to 2 meters and 70 centimeters. So a satellite that is operating in mode UV, that is UHF uplink and VHF downlink. Notice it says 70 centimeters up. If we remember our bands, that's in UHF, and the 2 meters is VHF, and that's in the downlink. What mode of transmission is commonly used by satellites? Well, you usually think of FM. FM is because it's VHF, UHF, but they also use single sideband, and they also use Morse code, and they also use data. A lot of information is sent up and down between satellites, so they use all the different modes. Excessive radiated power on a satellite uplink. If you transmit with too much power, then because you're basically desensitizing the receiver, other stations might not be able to use it at the same time. The satellite also transmits a beacon. It says, hello, 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 hello. I'm passing overhead. I'm passing overhead. And as it's doing that, if you can hear yourself, your signal should be about the same strength as the beacon station. LEO is low Earth orbit. The International Space Station is a low Earth orbit satellite because it's not geosynchronous. It's at about 220 miles. Geosynchronous is at about 22,000 miles. So there's a very big difference between geosynchronous or geostationary and low Earth orbit. Most ham satellites, of which there are actually hundreds up in space, are low Earth orbit. A satellite beacon is a transmission that contains status information. Here I am, here I am, here I am. All my electronics are good. Satellite beacon, it will contain health and status of the satellite. 32 degrees Celsius on board. Everything's good. Transmitter power is 10 watts. Everything's good. To receive telemetry from a space station, a satellite passing overhead, you do not need a ham license to receive. Anyone can receive. A satellite tracking program. Now, this is one of the really cool things that is available for almost no money. By knowing the Keplerian elements, this was basically the work of Johannes Kepler, who did orbital mechanics. By plugging in Keplerian elements, this will allow you to get a complete map of where a satellite will be and when it will be somewhere. So if you know where it will be and when it will be somewhere, you can aim your antennas overhead and talk through that satellite. Most things that are up in space, you don't actually even need to enter the Keplerian elements because they're already published. So if you go to a website called AMSAT, which I'm going to share in a second, if you click on the ISS, AMSAT knows where the ISS is and what those elements are. You give it your location, and it prints out a list of all the next overhead passes that you'll be able to see. Doppler shift. Has anyone ever heard a car going by fast or a fire truck? The pitch changes as it goes by. But the pitch changes because the waves as it's coming toward you are being compressed, so they sound higher. And as they're moving away, they have a longer wavelength, so they sound lower. This actually, because radio waves travel at the speed of light, we normally don't see this. But with a satellite like the ISS passing overhead at 17,000 miles an hour, it actually is noticeable, and you actually have to tune your radio for Doppler shift. As the satellite is approaching you, it sounds on a slightly higher frequency. As it's going away, the frequency drops. Similarly, because it's approaching you, you actually have to transmit on a lower frequency than you normally would when it's coming toward you, and on a higher frequency when it's moving away. So you have to take into account this thing called Doppler shift. Spin fading. The satellite, in order to stay stable, is rotating. Well, what if the antennas go from pointing at you to pointing somewhere away? If they're pointing away from you, then all of a sudden you won't hear it anymore, and that's known as spin fading. And we're going to take a break. Right before we do that, I'm going to pull up the AMSAT website, and then we're going to take a 5-minute break. So this is AMSAT, and it's the Amateur Satellite Corporation. It's based in Kensington, Maryland, and they are heavily tied in with NASA on the International Space Station. And here's all past predictions. So past predictions. Look at all the different satellites that are up there. There are a lot of satellites up there. So just for the heck of it, let's look up for CN84, which we're going to cover in a little bit, the next 10 passes. So here are the next passes with the date and the time and the duration and acquisition and loss of signal and where it's going to show up in the sky and where it's going to disappear and how high up it's going to be. And this is all just provided free of charge. You grab your radio, you point it at you grab your little antenna, you point it at where you think it's going to be. You can run tracking software. There's one that I use called Skyview, and it basically superimposes the location of the International Space Station on the camera image that I'm seeing, so I can tell if I'm pointed directly at the right place or not. Okay. Everybody ready for a 5-minute break? See you back at 11?
Yeah.
Okay. right. Anybody have any questions? Anybody? Questions about anything? Hey, Kent. Oh, you're on the phone. Sorry.
So, Scott, sir, I have a question if you have a moment.
Yep.
I'm a mom. I did Civil Patrol and Search and Rescue when I was a kid, and I have two boys getting ready to do the same. I'm looking to also make an investment of a radio for our home. We're in Anchorage, so there are advantages to that. Where would you start with looking for equipment, and what would you outfit kids of those age ranges with, both
Well, how old are
individually
they?
and for the house?
How old?
11, 14, and 16.
Ooh, cool.
Yeah.
Well, something they're not going to lose. Or if they do lose, you don't worry so much about it.
Yeah, because they will.
They will. Yeah. Okay. Well, so I am also the technical advisor to a college radio club, and we're in the process of getting a high school radio club going. And here is my favorite radio. And I'll tell you why. And it's not sexy at all. And I'm going to pull it up right here. And this is my favorite radio for use as a loaner. And so you've got the main manufacturers. You've got a lot of Chinese manufacturers. I try to stay away from the Chinese ones.
Yeah.
But as far as the main manufacturers of what I would consider the more decent FM radios, Yaesu, ICOM, Kenwood, Alenco, and there's probably a couple others in there, but Alenco is probably the least well-known of all of them. But this is a dual-band handheld, lithium-ion battery, works really well.
Okay.
Most importantly, for $100, it's waterproof. So
we don't drop anything in the snow
that's
here.
right.
In Anchorage.
It's IP67 rated, so it's not submersible, but it's waterproof.
Okay, great.
So that's why I like, for handheld radios, that's why I like that radio. Like I said, it's not sexy at all, but it's very, very functional. And we bought 10 of them for club functions.
Great.
Just because it's waterproof and dustproof. And it's going to get beat up and thrown in a backpack. And
yes.
So.
Okay, thank you.
Go ahead, Kent.
You were querying me a second ago.
Yeah, well, JD asked if I'm the gatekeeper. So, are you? I assume I'm going to be the gatekeeper.
Yeah, I don't know what it's going to be. We're going to form up early, of course, get organized, and then we'll sort that out. If you want to be the gatekeeper, the guy who makes the phone calls, that's great.
I can do that. You've got them. So JD mentioned something about 19 good to go. I thought it was more than that.
Well, there may be. Just looking at it here, just a second here. There's 19. Yeah, there's 19 applicants on exam pools.
Okay. I see that.
There were
I guess
up to 21. A couple of people dropped off because they didn't feel as though they were ready to test.
Okay. So if anybody else wants to sign up, there's still open spots. Just pointing it out. As of right now, we've got 19 signed up to take tests. So
I got 4 people that need to test early: Chris, Jeff,
Okay.
Eric, and James. If there was somebody else that needed to test early, speak now or forever hold your peace, because I'm going to get off there.
and make sure that we have your best phone number at which to be reached. And again, everybody is not going to be called at the same time because that would break the system. So even though the test starts at 12:30 Pacific, we're going to be going probably until 2:30 or 3 o'clock. So that's why we say if you need to go early or you need to go late, let's say you live in, Florida, and you need to go because it's going to be, you need to go early because by the time we're done, it might be 6 o'clock your time and you have to go somewhere. That's the kind of stuff we want to know.
Quick question.
We've got about.
Go ahead.
Go ahead, Ken.
No, I was going to say, just so everybody sort of understands the mechanics of this, there has to be at least 3 volunteer examiners to administer the examination. I've got about 20 VEs, okay, but there's about 20 of you. So you can do the math. So you see it takes like 30 to 45 minutes typically to complete an exam session for an individual. So you can kind of do the math and see we can't do you all at once. Okay.
How do we, when we're, so we do the examination, how do we put in for a custom call sign?
Okay, that's the vanity program. Okay,
Yeah,
so the
we're
first
actually
thing
going
is
to cover. We're actually going to cover
very
that.
good.
Oh, okay. Copy. Thank you.
We'll just say that's a later thing, Eric.
Yep.
And that's between you and the FCC, but Scott's going to explain.
Understood. I just
Anything
didn't know
else?
if that was something we needed to get in front of
Nope.
today. So,
Nope.
okay. Thank you.
Anybody else, anything for Kent before I bail off here?
Thank you, Kent.
I guess so. Thanks. Sorry to interrupt you guys. Good luck on your exams today. Thanks for being.
See you, Kent. Okay, here we go. We're back to this. Okay, so we're in what I would call the home stretch. So we're going to be going pretty quick, but that's okay. Operating activity involving contacting as many stations as possible during a specified period. That is my favorite activity on the air, known as contesting. Basically, this is radio sport. It's for those of us who are competitive. And we start every contest with a clean slate. Some are an hour long, some are 48 hours long, some run an entire year. So when making a contest contact, there are a lot of contests that go on during the year, and you're probably not going to know them all. If somebody is calling CQ contest, that means they're involved in a contest. If you're going to participate, you need to know what the exchange is. Exchange is just basically the information that gets passed from person to person. So for a particular contest, it might be your signal report and your zone, like your CQ zone. So you have to go look up where you are and what your CQ zone is. It might be the whole signal report after the call sign is 593. Really fast. Some others, it might be really long, but you have to know what it is before you participate. Go ahead, Isaac.
So I have a question because me and my grandpa have done this before. Have you ever gone on a fox hunt?
Yep. We're getting to that.
Okay.
Anna?
What's your call sign?
N7JI. It's right there on my little box.
Okay.
Okay. Good procedure when contacting another station in a contest. You send only the minimum information. Okay, what is a grid locator? So one of the things that I sent everybody in the packet that I sent out is a grid square map. And the grid square map looks like that. Everybody see that? That is the grid square map for the U.S. and southern Canada and northern Mexico. The entire world is split up into grid squares, which are actually rectangles. They're 1 degree in latitude by 2 degrees in longitude. And then within each one of them, for instance, DN 34 on the Idaho-Montana border, each one is broken up into 24 by 24. So you can actually go further down from DN 4, let's say DN 34AA to DN 34XX. And the reason that we do that is because it makes it a little easier to handle the granularity of pointing an antenna. For instance, if we are, oh, stop it. There we go. Let's say we're pointed at, let's say we're in Oregon. Oh, stop. I don't want to do that. all of a sudden there we go. So if we're pointed in Oregon in CN84 and we hear another station that says, I'm in Oregon, well, they could be north, they could be south, or they could be anywhere to the east. So by going a little further and saying, I'm in CN02 or CN92, that tells me where to point my antenna. Okay, which of the following methods is used to locate sources of noise interference or jamming? That would be radio direction finding, also known as fox hunting. So a fox hunt is where you take a transmitter, typically very low power, and you hide it somewhere. And people use directional antennas, such as, like, for instance, a 3-element tape measure Yagi. And I'm going to show you one. And here's a tape measure Yagi. I got to share that. Anyone guess why it's called a tape measure Yagi?
Use a tape measure?
Because you use a tape measure. That's right. You solder the tape measure. I've built tape measure Yagis. They work really, really well. They're actually good for transmitting as well as receiving. And because they're tape measures, you can actually roll it up or fold it up quite easily. They're really inexpensive to build because who doesn't have a broken tape measure in their house? I think everyone has a broken tape measure. So what you do is you just cut it up and you sand down the edges and dip them in a little bit of something so they don't cut you. And then you sand the back of it and solder it all up. And
We
you got
just
yourself
threw
an
one
antenna.
away.
Did you?
Yeah, it had some shards on it, and when you roll it in,
Yep.
it gouges.
Well,
I
you
wish I-
gotta go fish it out of the trash.
Well,
Or
recycling.
buy
yeah.
one for $1 at Harbor Freight.
Or sometimes they'll actually have free ones at Harbor Freight.
Yeah.
How do you keep the tape from rolling up?
Huh?
How do you keep the tape from rolling up?
Well, I mean, if a tape measure, if fully extended, it's going to lie flat.
Yeah, back in the 1970s, I was working as a biologist in Yosemite, and we used these little Yagi direction finders to locate our bears that we radio collared.
Exactly right. So we do this for fun. We do this also for direction finding. All of this is for practice. Let's say that somebody's interfering with something, or there's a transmitter that's interfering with something, and it's by accident, and people go out with their antennas and they can track it down. This is also very useful for emergency preparedness and for search and rescue. You know, somebody has an EPIRB beacon, they get covered in in an avalanche, and you can hear it, but you don't know exactly where. So you learn your radio direction finding techniques. Go out with search and rescue. It allows you to find the person easily.
Scott, question on a lot of light aircraft, you'll have an ADF, automatic direction finding, that uses a loop style antenna. Now, I haven't seen that in ham at all, where it's giving you a compass bearing to the transmitter. Is that something that, or is it just a lot more common to just kind of swing an antenna around until you hear it louder?
Well, I mean, as far as I've done, yeah, it's easier. It's more common to have an antenna that you swing around. But I'm looking at what you're talking about, and I don't know. I assume if you're familiar with, are you familiar with VOR?
VHF omnidirectional radios?
Yeah. The fact that they're actually a whole VOR system is a very complex means by which you have like a rotary antenna and then stationary antennas, which are electrically shifted.
So the signal it's homing in on is far more complex than just a simple beacon out there somewhere.
If ADF is, if that's what ADF is listening to, if it's listening to VOR, then yes.
Okay, copy. Thank you. That makes a lot of sense.
Okay.
So is it called fox hunting because you can aim the antenna and pick up something?
No, it's called fox hunting because we think like, I think it really comes back from the great British sport of fox hunting with dogs, where there's this, fox out in the woods and, out in the field, and the dogs go after it and try to find it. I think that's where it comes from. We actually call them bunny hunts here, or sometimes duck hunts, or being at the University of Oregon, call it duck hunts.
Gotta do ducks, yes.
Yep. Okay, so for a hidden hidden transmitter hunt, you want a directional antenna. Sometimes you don't even use the directional antenna, just for fun. VoIP is Voice over Internet Protocol. We use that a lot. There's also something called IRLP, which is the Internet Radio Linking Protocol. This is a way to connect radios, repeaters, and other electronic devices to each other over the internet using digital radio or digital audio. Echolink is another system that is a digital audio system. It uses analog, but once you have an Echolink ID, if you have a call sign and you register, it allows you to install the Echolink app on your phone or on your computer, for instance, and use Echolink to connect to connected repeaters and other hams all over the world using the internet, and be able to have a signal that then you can have pop out somewhere in the world, and you can be talking on a repeater from your hotel room in Norway, which I've done.
Scott, I noticed online somewhere yesterday, I looked it up. It sounded like it was maybe kind of fading, in lieu of newer stuff.
What, Echolink?
Yeah.
Oh, I use it all the time. A lot of it depends on what's available. I mean, we have an Echolink node on our repeater here, and since we have a lot of nets on our repeater, we have people who travel, like myself, check in from all over the place to get into their local nets from the road.
Okay, I'm not sure I saw that. Maybe it wasn't anything.
Yep, and here is Echolink. It's pulling up a list of all the repeaters, and as of right now, there are 6,128 of them online. So, of which
your phone is. Oh, sorry.
Yeah, you use your phone. You use your phone in lieu of a radio. So your phone connected to a Wi-Fi or cellular connection, and somewhere, typically near either directly at the repeater or at another radio that is tuned to the repeater frequency, there's a gateway that goes from the internet to the radio, and when you key up the Echolink phone, your signal is transmitted over the repeater.
Wow.
Like I said, we use it all the time. It's very, very active, at least even for just, at least for our repeater here. How is access over the air to IRLP? Again, that's Internet Radio Linking Protocol. You use DTMF. So every radio that you get, every handheld will have these buttons, which look a lot like your old school touch tone buttons. Well, if you haven't hit the transmit button, they're not going to send touch tones. But if you are holding the push to talk button down on the side, these will actually transmit touch tones over the radio. The right sequence of tones, if you have let's say you've paid your dues to the club that runs that particular repeater, will allow you to access IRLP and connect your radio through that repeater over the internet. An amateur radio station that connects other amateur stations to the internet is known as a gateway. And we are now on to rules and regs, page 108. Okay, rules and regs. Who runs amateur radio in the United States? That would be the FCC. FCC, Federal Communications Commission. Okay, so now Part 97 is the section of the FCC rules, Code of Federal Regulations, that governs amateur radio. And I don't remember if I included it here or not. So I'm going to, while we continue talking, I'm going to pull up FCC Part 97. And here is FCC Part 97. You can get it from the FCC. You can also get it from the ARRL, which is the American Radio Relay League. And the ARRL is the organization that is responsible for administering, or I should say for managing, amateur radio in the United States and is a member organization as opposed to the FCC, which works for the government. So of the roughly 800,000 hams in the United States, about 160,000 belong to the ARRL, pay our dues, and they're the ones who, when something comes up in front of Congress or new legislation comes up that the FCC is trying to work out, which is an agreement between, let's say, the hams and the cellular communication companies and NASA. The FCC, the ARRL is the group that goes and represents us. So it's a very worthwhile organization, if only for that. They also do all kinds of training, accrediting, scholarships, and stuff like that. But anyway, they're the ones who are our voice in front of legislative action. So the next question covers, why do we exist? So we haven't really covered this. There are 5 reasons why we exist per the FCC. Because if you think about it, we're given access to all these different frequencies and basically free run of all these different bands, right? Those bands are worth money. They could lease these things out for billions of dollars a year. So why don't they? The reason being that we've existed for, as a group, hams have existed for 120 something years. We were the experimenters who came up with a lot of the technologies that we use today over the air. There's communications in a lot of parts of your life that you never really think about. I mean, people just grab a phone and they don't really think about what is inside it and what is allowing them to become part of connectivity to other places. Just the concept of Wi-Fi, right? Wi-Fi is an amazing thing. The internet, it had its roots in amateur radio. The protocol that's used for internet traffic came out of radio. It was single sideband was developed by hams. Before that, it was all AM. So here we go. Recognition and enhancement of the value of the amateur service to the public as a voluntary, non-commercial communication service. This is actually codified in the FCC rules that we are non-commercial, no money. So we do it for free. We do it because we like it. We are expected to give back. Notice that, public, amateur service to the public, providing emergency communications. When the chips are down, they're expecting us to know what we're doing. Continuation and extension of the amateur's proven ability to contribute to the advancement of the radio art. We've done this continuously for 120 years. The goal is that we're going to continue to do that. That's why it behooves everybody who is interested in amateur radio to push further, to never really sit still and always try new things. Encouragement and improvement of the amateur service through rules which provide for advancing skills in the communication and technical phases of the art. That means we come up with new rules. We're trying to push one right now for symbol rate versus bandwidth, because symbol rate and bandwidth are not the exact same thing. We've developed more bandwidth efficient methods of communicating digital data. So we're trying to get that codified. Expansion of the existing reservoir within the amateur service of trained operators, technicians, and electronics experts. Do you know what one of the hardest places to recruit people into is these days? Broadcast engineering. There are broadcast engineers who have worked their entire lives. Most of them are hams. But a broadcast station operates 24 hours a day, 7 days a week. If somebody is on call, who wants to do that job, right? And their responsibility is, if anything goes wrong, they got to go fix it. And if something happens, they're responsible and have to answer to the FCC. So there are a lot easier ways to make a living, but there are still a lot of reasons for broadcast to exist. I mean, there's over-the-air radio, there's over-the-air television. So notice this: electronics experts, operators, technicians, and electronics experts. Who repairs the equipment in an airplane? Who is qualified to repair aircraft avionics and aircraft communication systems? You know, in a lot of cases, it's hams who, in addition to doing this as their hobby, do it as a career. So this is a good place for us to develop the future skills that are needed to keep things going in the world, really. And finally, continuation and extension of the amateur's unique ability to enhance international goodwill. Even during the Cold War, when there were a lot of countries who the United States was not particularly friendly with, amateurs are a non-political, non-commercial entity, right? We are not our governments, we are people. And our governments may not agree on things, but it's a chance for people to get to know each other better. So I have lots of friends who lived in Eastern Europe. I have lots of QSL cards from contacts I made in Eastern Europe. You know, you think, okay, well, we're not so friendly with China. You know what? There are thousands and thousands and thousands of hams in China, and I contact them all the time. So again, you know, people are different from governments. So ham radio is one of those places where we can continue to be so. Okay, so that's the reasons why we exist. One of those will possibly show up on your test. What is the FCC Part 97 definition of a beacon? A beacon is something that says, here I am, 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 transmits continuously and never expects a reply. So propagation or related experimental activities, saying, here I am, here I am, here I am. And if somebody can say, oh, I hear that, that means that there is a communications path that exists between 2 points. A space station is anything 50 kilometers or higher above the Earth's surface. That's the definition of a space station. When are you allowed to interfere intentionally with another station, even if they're really making you mad? And the answer is never.
Never.
We are not allowed to intentionally interfere with anyone. Which of the following entities recommends transmit and receive channels for auxiliary and repeater stations? So remember I brought up that ORRC, that Oregon Radio Relay Council? That is a volunteer frequency coordinator. That is the organization that is responsible for keeping the peace by setting up a band plan or a coordination plan for how to use these frequencies. Amateurs in a local or regional area whose stations are eligible to be repeater or auxiliary stations select the unlucky person who gets to be the frequency coordinator and has to deal with all the arguments. So if somebody says, I just built a repeater, I'm looking for a frequency to put it on, I'm going to go ask the frequency coordinator, and I hope the frequency coordinator doesn't say no, but the frequency coordinator is responsible for making that choice. Okay, frequency allocations and power limits. This is where it's really important to take a look at this chart. As a technician class operator, you are allowed 6 meters and up, complete access to any frequency that is on the chart, 6 meters and up. Now, there are some other, with a very few exceptions, you are allowed to transmit, and this is why it is important to have something which is a licensing process, 1,500 watts of RF power output. That is a lot of power. And now that we understand what that means, we're going to add a little bit of something to that to understand just why it's so important to have this licensing process. Okay, so is there a limit to how much gain you can build in an antenna?
No.
Not really, no. So let's say that you make a dish antenna, which you get as a repurposed TV satellite dish, right? You can get repurposed TV satellite dishes, and this is 5 feet across. And you connect it, you put a little transmitting antenna inside, and you connect this to your transceiver down here, right? Do you see any problem with that yet? I don't.
No.
Nope. And you have a power supply right here. And you connect that to your transceiver, and you have 1 watt of transmitter power, and you have a forward gain of 30 dB. Okay. How much is 30 dB? Thinking back to yesterday. What
Times
is
1,000.
Yeah, 30 dB is 10 plus 10 plus
10
10,
plus 10
which is 10 times 10
times
times
10
10,
times 10.
which is 1,000 times.
1,000.
So what is your effective radiated power in the forward direction if you're running 1 watt?
1,000.
1,000 watts, yeah. So it's like you're running 1,000. If you had an antenna that was transmitting in all directions, it would be the same as running 1,000 watts. I would not want to be standing right there in that case, right? I don't think anybody else would either. But
No.
what is the legal limit? It is not 1 watt, is it?
No.
So I could go and build a power amplifier that was a kilowatt. Okay. So now, how many times is my antenna multiplying my signal? It's still 1,000 times, right? So
Wow.
what is my new effective radiated power?
1,000 million.
It's 1,000,000 watts, or 1 megawatt of effective radiated power. When would you use something like this?
When you want to kill somebody.
Well, right. Or if you, or let's say that there's this celestial body right here, which is 250,000
moon.
miles away, like the moon, and you want to bounce signals off the moon. We use something like that for moon bounce. And we send signals and we bounce them off the moon, and they bounce back. They bounce in this direction, they bounce in this direction, and other people around the world can pick them up. Are you allowed to do Are you allowed to do that with a technician class license?
I don't think so.
Absolutely.
Oh,
really?
Yeah, really. That's why there is such a thing as a licensing procedure, because if used improperly, you can cause a lot of damage. You can hurt somebody really badly. So,
Hey, Scott,
yes, Kent.
what I noticed, I worked on Rother over there in the Aleutians back in 1980, a relocatable over the horizon radar system. And we set up on the north end of the island the antenna array, and then at the south end of the island, we put in the receiving array.
Yeah.
And they, I guess, bounced it off the ionosphere. The one problem they had when they hooked it up was really cute. The power was going too fast from the generator plant to the receiving plant, and they kept blowing the thing up. They had problems with their power lines. And I was just curious as far as the over the horizon effect and stuff like that.
I don't really know. I do know that. Have you ever heard of something called HARP?
Yeah.
If you live in Alaska, you've heard of HARP?
Yes.
Yeah. They still use HARP, but typically it's used for really experimental stuff now, as opposed to military. So, the high altitude atmospheric research program, they basically make their own ionization by pointing a radio at the sky. Big antenna.
Make an artificial aurora.
Yes, they do. Artificial aurora.
We've been fortunate. We've been actually the Anchorage Club at the Radio Science and Operations Center. We've actually participated in several experiments with people doing experiments at HARP. It's been really cool.
So the one thing we had that was questionable out there is after we built it, they put an 18-man camp up there, one of those construction site, what do you want to call it, modulars. It was only 20 feet back from the antenna array. And we were questioning that if that was safe.
Depends which direction they're pointing it.
It's pointing towards Russia.
It's probably fine.
I was worried about the backside.
So I have a question. So I got a note from JD. Is Jeff Logan, are you registered?
I'm here, sir. Yes.
Are you registered to take the test?
No.
You're not. Okay. Okay. So he is not. Okay. So somehow JD has your name, but he is.
Yes, I chatted with him.
Okay. Okay. Kent, you got anything else?
No, I was just coming in to
Dropping
check
in?
with Jeff because.
Oh, okay.
I was coming in to check with Jeff as well because we chatted earlier and he said he needed a test early. Unless I was confused. And then we checked, was like, hey, Jeff's not on the list. So, okay.
Sorry, couldn't reply. I was busy taking notes.
Okay. All right, let's see. Continuing on. So now this is where it's really important to look at the frequency band plans. I'm going to be bouncing back and forth a little bit. So first question, what frequency is in the 6 meter band? We'll look at the 6 meter band. See that 6 meters covers 50 to 54. So the choices of those would be anything within 50 to 54. And we would find that 52.525, even though you look at it and say, well, 49 is closer to 6 meters. 6 meters would be exactly 50 megahertz. This is where it's really important to know what frequencies are in what bands. 146.52. 146.52 is the calling frequency, very special frequency, right here in the middle of the 2 meter band. On what HF band does a technician class operator have phone privileges? This has been very exciting lately because we have a lot of sunspots. We have really good solar activity. And you'll notice this little blue hatched area right there. And that says novice and technician voice. So there you go. You have access on the 10 meter band, specifically from 28.3 to 28.5. And it's been a lot of fun lately. Lots of international and domestic contacts to be made.
What's that, Scott? Is that like a phone patch?
No, that's single sideband.
Oh, okay.
Yeah, regarding phone patch, not a whole lot of people use phone patch anymore because not a whole lot of people have wired phones anymore.
Right.
And yes, phone is voice. It comes from telephony. So that's why we call it phone. So, where may SSB phone be used in amateur bands above 50 megahertz? That would be, if we look up here, you look at single sideband, you notice that every band 6 meters and up has some of that kind of like an olive green color. So every band 6 meters and up has at least some room for single sideband. Which of the following UHF, VHF band segments are limited to CW only? There are 2 of them. CW only is the red. There's actually 3, but they didn't ask about this one. So it's 50.1, 50 to 50.1, and 144 to 144.1. And those are codified. Those are Morse code only parts of the band. Now, there's also one band that didn't even really make it on here. One part of one band. Notice that 1.25 meters, or we call it 222, goes from 222 to 222.5. There's actually a disconnected section of this band that goes from 219 to 220, which is kind of the black sheep of this of VHF UHF. What happened was, a long time ago, I believe it was UPS came along and said, well, we've got this project and we want to use 2 megahertz in the 220 to 222 band, and we know that's a ham band, but how about they don't use it that much, and we'll give them 219 to 220. And it was decided, okay, UPS, you can do that. And so we ended up with this section 219 to 220, and that is used for fixed digital message forwarding systems only, which is kind of a weird thing to say, except that it's basically, digital information. It's packet radio from point to point. So we still get to use it, but it's kind of a weird band. Why should you not set your transmit frequency to be right at the edge of an amateur band or subband? So in order to show you this, what are the rules regarding our use of a frequency band? So let's say this is 28.3 to 28.5.
Stay inside the lanes.
Stay inside the lanes. That's right. You are allowed to go all the way to the edge, and you can be anywhere inside. So let's say, everybody, how wide is a single sideband signal in kilohertz?
3.
3 kilohertz. Okay. So this is 28.500 or 28.500 kilohertz. This is 28.300 kilohertz. So if you are on upper sideband, you have to know that your signal looks like this. Here's your center frequency, that's your dial frequency, and how far above will it go?
3 kilohertz.
3 kilohertz. So if I tune my radio to 28499, where, if I draw that signal, where will it be? Is it inside the lanes anymore?
No.
Nope.
2852.
That's right. So
Leaking.
So you would not really tune your radio above 28497 for that reason. So the reason that we do that, the reason that it's so important to understand the rules is because, and to not set your radio too close to the edge, your transmitter might drift a little bit while you're transmitting, and it started off in the band, but now it's not. The other one is that, okay, modulation sidebands don't go beyond the edge. If you're really loud, then some of it splatters over the edge, for instance.
Yeah.
And finally, your frequency display might be off a little bit. So if you are off by 1 kilohertz, for instance, you think you're in lane, but you're not. Okay. The entire 70 centimeter band is one of those places where we are a secondary allocation. Primary allocation has the first right to be there. Secondary, if we're secondary, somebody else is primary. That means that a primary user could actually kick us off. So the 70 centimeter band, military is primary use. We're secondary. We've never been completely kicked off 70 centimeters to my knowledge, but if there was a national emergency and they said, look, we really need to use 70 centimeters, you can't interfere with us, you need to shut everything down, they could actually do that. There's actually also areas of the U.S.-Canadian border where the Canadians don't have access to the entire 70 centimeter band. And if we're within, I believe, 100 miles of the border, we're not allowed to use that part of the band because we're not supposed to interfere with their operations. So, yep. Okay, so if there's a primary station that we don't recognize, but they're part of the primary service that's allowed to be in a band and we are not, then we have to keep quiet, not interfere with them. Except for some specific restrictions, the peak envelope power for technician class operators is 1500 watts. Again, 1500 watts is a lot of power. That's why you're getting a license. If you're on the HF bands, for the most part, your limit is 200 watts. I don't ever run more than 100 watts, and really, I really hardly ever run more than about 30 or 40 watts. 200 watts is still a lot of power. You can make a lot of contacts with 200 watts.
Why is that about? What is that about HF that?
Well, I think a big part of it was that novices a long time ago were limited to crystal operation. And because part of the incentive to getting licensed was that when you upgraded your license to a higher class, you could run more power. So the limitation is still there. So that and the fact that, you know, locally, okay, you can run a lot of power on VHF and UHF, and your interference doesn't go all that far. However, if you are on, you know, HF and you're running a kilowatt and the band's open, everybody can hear you. There are 3 classes of license available from the FCC: technician, general, and amateur extra. No, I don't know why it's called amateur extra and the others are not. We just call them technician, general, and extra, but the technical term is amateur extra. An FCC license is good for a period of 10 years. We used to get things in the mail saying, congratulations, here's your license. You don't get that anymore. You can log on to the FCC's website called the FCC ULS. You can check to see if your license is listed. You can also sign into it and get an official copy of your license to put on your wall if you want it.
Today, the test is the technician test.
Well, I mean, that is the first test. That's what you're studying for.
Yeah.
Yeah. I mean, if you're ready to take the general and the extra also, you could do all 3 at one time. But you have to pass them in order. You're probably not ready to do all three. I don't know that anybody here is ready to do all three. Although I did actually once have an engineering student who came in, did this class, and he walked out, electronically walked out with an extra class license. I said, yeah, you're an engineering student, aren't you? It's like he's a senior electrical engineering student at Portland State. And he did a little bit of extra studying. And he said, yeah, with an electrical engineering degree, the rest of the stuff isn't really all that hard. So, okay. So once your license shows up as being active in the FCC's database, it is a valid license. You're allowed to hold one license. And what proves that the license is active? It shows up in the database. Don't even have to have it on paper. Okay, so the vanity call sign. Vanity call sign program, any licensed amateur can apply for a vanity call sign. The license, the call sign that you apply for has to be allocated to your license class. So for instance, if you wanted to apply for, let's say your name is Pete Castor. I'm just taking you for an example. Your initials are PK. You wanted to apply for K7PK or K2PK. You could apply for it, but it has to be that you had an extra class license because that is a 1x2 call sign. The way we refer to call signs is that every U.S. call sign has a number from 0 to 9. It has a letter or 2 before it and 1, 2, or 3 letters after it. So, for instance, N7JI, that would be a 1x2 call sign. K7ABC is a 1x3 call sign. AA7AR is a 2x2 call sign. KA9RRR, that's a 2x3 call sign.
What would KC9BMA be?
That would be, you tell me.
3 by
There's
3.
2.
Oh, 2.
That'd be a 2x3.
Oh, 2 by 3. Okay.
Right. So as a technician or a general class licensee, you can apply for 1x3s and you can apply for 2x3s. As an extra class operator, you could apply for anything that is a valid call sign. So 1x3, 2x3, 2x2, 2x1, 1x2. There's also a call sign which is 1x1, like N7W. That's a special event call sign. Those are only handed out on a temporary basis. So you can also pick a call sign when applying for a vanity call. You can pick any call sign independent of the area in which you live. So if you, let's say, I don't remember if I sent out a map or not. So here's the United States. So here's the U.S. call sign map. And notice that we have all the different regions of the United States separated out. Depending on where you live, that will determine what your sequentially assigned call sign will have as far as a number goes. So you live in Indiana, you'll get a 9 call. You live in Iowa, you'll get a 0 call. You live in Nevada, you get a 7. You live in Texas, you get a 5, and so on and so forth. Once you apply for a vanity call sign, for instance, you can pick any number from anywhere. But you have to keep in mind that when you do so, it might be a little confusing if, for instance, like my wife, her call is K3LUX. You look at the 3 calls, they're from Pennsylvania, Delaware, Maryland, and D.C., but she lives in Oregon. There's another ham out here who's quite active. Her name is K9JOY. She lives in Oregon, but the 9 calls are Wisconsin, Illinois, and Indiana. So, it can lead to a little bit of confusion, but it's perfectly okay.
It's kind of like the telephone codes, right? I mean,
It is now, yeah. They're all
you know,
mixed up, and you
yeah.
take your phone from wherever you get it. And so that's why, so now you notice we have this, which of the following is a valid technician class call sign format? W1XX, that's a 1x2. KA1X is a 2x1. KF1XXX, Anna, what's that one?
That is a 2 by 3.
That would be a valid call sign. So, and the other thing is that United States call signs all begin with W, N, K, or AA through AL. Those are the prefixes that we are allocated in the United States.
So
I'm sorry if I missed this.
Oh, sorry. I'm sorry.
Go ahead.
Go ahead.
As far as applying for a vanity license, do we have to wait for a automatically assigned one and
Yes.
then apply?
Yes.
Okay.
But you can apply the very next day. You can apply the very same day. So what's important to note is that the call sign that you apply for has to, if it was previously assigned, it has to have been vacated or expired for a period of 2 years.
And what about K versus W? I mean, the reason I'm asking is I talked to JD and I had a novice license back when I was in high school in New York. So that was a WN2.
Yep.
And he said, oh, you could probably get that because it's not in use. Well,
Nobody
I probably
else is going to want it.
Yeah, it's not the slick. It was WN2 SII. It doesn't really roll off the tongue.
And it's not a great Morse code call either.
Yeah. So
because it's got a lot of dits and that gets a little confusing.
Yes. But the question is, I mean, K versus W. K is West Coast, W is East Coast.
Only for commercial TV and radio stations.
Okay, Scott, question is, sorry if I missed it, is there's a hierarchy to the number of characters in the call sign? For example, the amateur or a lower technician class would have more characters than.
Yep.
No?
Yep.
Yes. Okay, I missed that.
So a technician again is a 1x3 or a 2x3. Those are the only call sign formats that are available to technicians and general class operators. The higher the class license you get, the fewer the letters you can apply for.
So you get different call signs through your life?
You can. I've had 3.
Okay. When you go from technician to
you're never required to change.
Do
You're
you
never
have to
required to
change?
change. If you like your call sign, you can keep it.
Okay.
Let's see. Grace period is 2 years. So you're not allowed to operate on an expired license, but it doesn't completely disappear for 2 years. You have to wait till it's been renewed. A club has to have at least 4 members. If you don't keep an email address with the FCC, they try to get a hold of you, they can actually revoke your license. So they have to have a valid email address. Now they also need to have a valid mailing address, so that if they try to send something to you and it's returned as undeliverable, then they can pull your license for that too. They always need to be able to get a hold of you somehow. From which of the following locations can you transmit with an FCC call sign? Either in the United States or any boat that is registered in the United States and in international waters. So if you're on a boat that has U.S. registry, that's part of the United States. When are you allowed to transmit indecent or obscene language? The answer is never. When are you allowed to transmit music? The answer is almost never, and practically speaking, it's never. This came out of the fact that we used to rebroadcast NASA transmissions, and we used to wake up the space shuttle astronauts with music, and in doing so would transmit wake-up music that would be rebroadcast over the ham bands. So unless you are waking up astronauts, you're not allowed to transmit music. Now, if you're at a music festival providing communications and there's music in the background, or your kids are in the car and the stereo's on, that's probably okay because you're not transmitting music for the intent of transmitting music. Let's see. When is it permissible to transmit messages encoded to obscure their meaning? Typically, the answer is never. But let's say that you are operating a satellite or you have a remote controlled craft like a drone. You really don't want somebody else to take over your drone and crash it, or deorbit your satellite and crash it into the ground. So you're only allowed to encode messages when you are transmitting to space stations or remote control craft. Other than that, we're not allowed to obscure any meaning. And that means you're not allowed to speak in spoken codes either. So you can't have a few words that have a special meaning just for one other person.
What about foreign languages?
Foreign languages are fine.
Okay.
I have contacts in foreign languages all the time. With who are you not allowed to talk? Basically, if another country has said we don't like the United States and our hams are not allowed to talk to their hams. Believe it or not, this does not exist anywhere in the world right now. Even between the U.S. and North Korea. If there was a licensed ham in North Korea, I could talk to him. And so would all the other millions of people who have never contacted North Korea. And the ITU is the International Telecommunications Union, which is part of the UN, is responsible for keeping track of all that. When are you allowed to receive money for operating a station? And the answer is only if you work for, let's say, W1AW, which is part of the ARRL, or you are a teacher, and it's incidental to classroom operation. You can use ham radio to demonstrate physics. You can use ham radio to demonstrate communications and do all other kinds of cool stuff if you're a teacher and you're doing it in the classroom and still get paid. You're allowed to buy and sell ham equipment over the airwaves. You're not allowed to generally do business over the air, but you're allowed to buy and sell ham radio equipment that has something to do with radio, and if it's not on a regular basis. So you're at a ham fest, your friend finds a radio, and you say, hey, would you like to buy it? Yes, I would. How about 200? You can actually negotiate. Normally, you wouldn't be able to do that because that involves business, but this is not business. Broadcasting, the difference between transmitting one-way communications and broadcasting. They're both one-way. They come out of a central location. Broadcast is defined for the general public. One-way transmission is described as transmitting for the general ham population. So we are not allowed to, with very few exceptions, transmit for the general public. When are we allowed to? Is again if there is immediate safety of human life or protection of property. So we can actually help a news gathering, let's say a news station. We can provide them a communications link so that they can report. If that's the only way to get information back, they can report on the dam that's about to break. So what are we allowed to actually do?
I have a question.
Yes.
I've been meaning to ask this, but you just touched on the emergency uses again.
Mm-hmm.
And you said somebody was reporting a brush fire.
Yep.
But they had other means to report it. You
Yeah.
got hit with a $38,000. It just put me into all kinds of scenarios, like camping and a bear's attacking you and your satellite phone, you have one, but instead you're yelling for help because somebody got mauled.
Mm-hmm.
I mean, how often do they, when you're in full on panic mode because a loved one got hurt, how often are they going to slap you with something like that?
Probably not. But in this particular instance, it wasn't an imminent danger.
Oh, okay.
He just took it upon himself to try to direct firefighting efforts.
Oh, misunderstood.
Yeah.
Okay. I thought I heard that too, but then I thought he was just the first to report it.
No. It was
Okay.
not imminent danger.
Alrighty.
Is that an unlicensed person?
It was a licensed ham, but he also had, a radio that was tuned to the wildland firefighting frequencies. And he took it upon himself to go on to their frequencies and tell them when there were other ways to get that information across. That would have been
That was a $38,000 fine.
Got fined $38,000 for that.
Dang.
Is there any kind of arbitrary or anything you can do to fight that? Or
I'm sure you can always appeal. He probably appealed.
It's okay to listen to their band
yeah, sure.
as long as you don't talk, right?
Right.
Yeah.
And Scott, can you tell us, so they were able to identify him because he used his call sign?
Yeah, he told them who he was and where he was and everything.
Right.
Mhm.
Yeah. I mean, he could have just as easily picked up the phone and called the local office. That's the thing, and it was hard to justify because even he admitted he could have just picked up the phone and called the local office. So, the FCC takes incursions into other frequencies as a big deal. So, but I mean, if he was about to die, the thing was about to overrun him, then it would be fine. It would be perfectly justifiable.
Okay, thank you.
So what are we allowed to largely do? Most of the stuff we talk about is communications incidental to the purposes of the amateur service, those 5 things that we talked about, and remarks of a personal character. How are the kids? I got a doctor's appointment on Tuesday, etc., etc. I used to laugh at that. Now I live it. Now that I'm older. Okay, control operator and control types. We are almost there, and we're going to go a couple minutes over, but we're in the very last few pages. Okay, a control operator is the person in charge of a radio station, a ham radio station. A transmitting station may never operate without a control operator. Now, if there is nobody else listed, the control operator and the station licensee are assumed to be the same person. So when you get your license, you are a licensee of a ham radio station. If that station, like this is a ham radio station that I'm holding in my hand. If it's a piece of transmitting equipment, this is a ham radio station. I am the control operator. I decide whether or not it transmits or not. I am the operator that's in control. There are different types of control. If my finger is on the push to talk button, I am the local control operator. If something happens and this is allowed to be connected to the internet and I push a button on a computer somewhere and it makes it transmit, that is known as remote control. It's a remote control operator. If it happens automatically, such that it, for instance, receives something and retransmits it, that would be known as automatic control. Still, the person who has the equipment is the control operator and is somehow responsible for it and its proper operation. So if there's no, when do you have to have a control operator? And the answer is always. So you may never have a transmitting station without a control operator. So the station licensee designates the control operator. So let's say that I have my station and somebody comes in and I say, I'm going to walk out and go use the bathroom. If that other person is licensed, I can say, you're in charge. If something goes wrong, we're both responsible for it. So I'm the owner of the equipment. The other person is the control operator. We're both responsible. Sometimes they're the same person. Who is responsible if a repeater, what kind of control is a repeater operating under? It'd be automatic control, right? Repeater operates automatically. It receives something and retransmits it. It doesn't vet what's being said to make sure that it's legal or not. It just retransmits it. So if somebody is standing on the ground with a radio in their hand, transmitting into a repeater and starts shouting out all kinds of profanities, and it gets retransmitted by the repeater, it's not the repeater owner's fault, and it's not the control operator's fault. It's the fault of the person who initiated the illegal transmission.
So Scott,
Yep.
So a repeater has to be manned at all times?
Technically, it is. It's automatic. There's always somebody who is responsible for it. But because it's operating in automatic control, it's up to, it's going to operate. But if somebody says, hey, it's interfering with somebody and gets in control or gets in touch with that person who is listed as the repeater trustee, it's up to that person to shut it down. Figure out how to get it shut down.
But that wouldn't be considered being operating without an operator.
Nope.
I mean,
you're still the control operator, even though you're not physically present. Somebody's still ultimately responsible for how it works.
Okay. Thank you.
Mm-hmm. So if you have a technician class license, when can you operate in an extra class band segment, assuming that there's no big emergency? And the answer is never. So you can't be the control operator of a station operating outside of your limits. So if you're transmitting up to a satellite and it's being sent back down in an area where you don't have privileges, that's actually okay because you're following the rules and it's automatically retransmitting it somewhere else. So even though you pop up somewhere else where it looks like you don't have privileges, you didn't put the signal there and it's okay. So if you're allowed to transmit on the uplink frequency, then you're doing it legally. Okay, the control point. This is an amateur radio station. My push to talk button is the control point. The control point could also be the keyboard on a computer in a remote location. That would be known as remote control, and an example is operating it over the internet. So if you are operating over the internet, the control operator has to be at the control point. There always has to be a control operator, and the control operator indirectly manipulates the control. So you typically have a computer screen, you push buttons. That also means that if something goes wrong, you have to have the ability to do like a remote kill switch. Automatic control is repeater operation. And we are now into the final home stretch. Yay. Okay, station identification, repeaters, third-party communications. If you're licensed, you're probably going to, at some point, do third-party. You are required to transmit your call sign every 10 minutes and at the end, period. Unless, of course, you're transmitting to a remote craft. If you're doing remote control, like to a drone or to an RC plane or an RC boat or something like that, your transmitter has to have your name, call sign, and address and printed on it. And you're typically limited to 1 watt of transmitter power.
Can I ask, it says, when are you required? I thought you were also required when you first started your transmission.
Nope.
I was just going to say the same thing.
Nope.
Yeah.
Nope.
No?
Nope.
I thought that was how you got it, broke into it. But this is...
It's customary, but not required legally.
Well, how about when you're replying to somebody? You said to...
What if you know them really well and they know your voice? That will happen frequently. Like I'll have somebody like who calls and says they're listening, and I'll say, "Hey, Jim."
I'd say, "Who's this?"
Oh, they'll know who it is because I've talked to them 100 times before, 1,000 times before.
Okay.
Different.
So if someone,
different.
If I start talking and I don't say my call sign, and they say, "Who is this?" I'm not legally required to say who I am.
Nope. Not until 10 minutes goes by.
Wow.
Now, I would still do it at the end. I mean, I would still do it at the beginning just because I like my call sign, but you are not required to do so. It's at least every 10 minutes during and at the end.
Yeah, but you're going to eventually have to identify yourself because you're going to end the call.
That's right.
Right.
But you don't have to do it at the beginning.
Okay.
Okay.
Yep.
Wow.
That's the rules.
Wow.
Yeah. Again, I would still do it at the beginning just because. What language in the United States? Oh,
legally, at the beginning, you don't have to identify yourself when you're talking. So you have to keep track of the time you're on in order to do it at that first 10-minute.
Yep. You got a clock in your head. The easiest way to do it is to do it. The easiest way to do it is to do it too frequently. But I think that everyone who's licensed and has been on the air has gotten into conversations that go back and forth where they sort of lose track of time. And at some point in your head, you have I got to identify. Little buzzer that goes off.
Oh,
you know, there's like a little clock that goes off, and some people actually, they'll have if it's like a big station, we used to have a lamp that said identify, big bright red lamp. And when you identified, you pressed the foot pedal, and then after about 9.5 minutes, the light would come back on to remind you to identify.
Glad I asked that.
Yeah. So, and in today's world, you can build it with an Arduino. So
what happens if you forget to?
Well, I mean, you're technically operating illegally. So you just have to sort of keep it in mind. I mean, we've all done it at some point. At some point, I think, oh, it's been a while. I wonder when the last time I did it was. Then you identify, and then you're good. In the United States, you identify in English. If you're in a foreign country, you follow their rules. I've identified in Spanish. I've had conversations in Spanish in the United States where I identify in English. If I've been in Spanish-speaking countries, I've had conversations in English where I had to identify in Spanish. How do you identify during a phone emission? Phone is voice. You can either say your call sign, N7JI, or you can use Morse code and send your call sign over Morse code. Phonetic alphabet is encouraged because it eliminates confusion. And there's also something called a tactical call sign. Tactical call sign is a temporary call sign that you would use to identify yourself, like race headquarters or aid station 2. But that does not eliminate the need to identify using your actual call sign, because race headquarters is not an FCC call sign. So you would say aid station 2 N7JI every 10 minutes and at the end. And let's see. Self-assigned indicators like N7JI /W3, slant W3, stroke W3, those are all valid. They're for basically self-identifying the fact that you are not operating in your normal location. Third party. A third party is somebody who is a third person. So if I am talking with another licensed ham, a third party is somebody else who I am transmitting messages on behalf of. That could be me actually speaking what they want me to say. That could also be me handing them the microphone and being ready to smack it out of their hands if they say something I don't want them to. So, but either way, it can be their own voice or it can be traffic that's being passed on behalf of a third party. Dealing within the United States and Canada, we always have third-party agreements. They're fine. You can get little kids on the air. We do it all the time from our museum station. And if you're dealing with other countries, the United States has to have a third-party agreement in existence with that foreign country in order to allow a third-party message to go across. And finally, if the FCC knocks on your door, we are on page 123. If the FCC knocks on your door, they're typically not going to. But if they want to look at your equipment, they think that there's somebody, they did some direction finding, and they think that you're interfering with the local air traffic control station. They want to look at your equipment, you better let them in. So if the FCC shows up, again, very infrequently, you got to let them in to inspect your stuff.
Thanks.
Excellent job, Scott.
Yeah, good class.
Thank you, Scott.
And I'll stick around for some questions. I know we don't
Thank
have
you, Scott.
we don't have tests for 20 more minutes.
What is 73?
7-3. It's actually from Morse code. It's the number 7 and the number 3, and it indicates best regards, plural.
Thank you, Scott, for your generous nature and all that you've done for us.
I appreciate the comments, and I
Thank
thank
you,
everybody
sir.
for doing this. So, any other questions?
Excellent job, Scott. How many languages do you know?
Well, let's see. I took French in high school and college. I taught myself Spanish because I was working in South America.
You know English.
I know English pretty well. I can read Hebrew. I know a little bit of German.
Sehr gut.
Ja.
Ausgezeichnet.
Du bist sehr klug.
Ja, sprechen
Ganz gut, Anna.
Sprechen Sie Deutsch keine? Oh, kleiner.
Danke.
Kleiner.
Ein bisschen.
Ein bisschen.
Bitte.
Yeah. And I speak Morse code fluently too.
Jim ist sehr klug und nett.
See, you're getting to my limits. I've worked in German-speaking countries though.
Very clever and nice, she said.
Ah, okay.
What state are you in, Scott?
Oregon.
Oh, that's right. Yeah, I'm in the state of confusion. Thank you.
Okay, I know that well. Any other? Oh, and I also speak a multiplicity of computer languages. So.
Yeah, same here.
Yeah.
Yeah, here too.
Scott,
Thanks, Scott. I appreciate everything.
You bet.
Great.
So I'll see some of you guys a little bit later.
Yeah,
during
you'll see
testing.
me.
And the other thing is that when you, even if you're not taking a test right now, stay in touch. Let me know how the testing process is going and stuff because.
Scott,
Yeah.
I have found out that there is a local group here. I'm up in the White Mountains of Arizona, and they are going to be giving a test towards the end of this month.
Cool.
So I'll be working with them.
Excellent. And so I strongly recommend, again, that the app, that ham radio exam app, which looks like, I don't know if it opens, which looks like that, and allows you to practice one section at a time. Because, to be totally honest, because the exam.
You sent.
Yeah, I included that
you
one.
You sent that to us.
Right.
Yes.
And I strongly recommend doing it that way because I know for a fact that the question pool is so large that if you take randomly generated tests, you could take 25 randomly generated tests and still never get every question. So
okay,
it allows you to focus on one area of learning at a time, and I think it's really helpful. Yeah.
Quick question. So right after this, if we sign up to take a test, we should be getting a call.
You should be getting a call in the next couple hours.
Okay.
So if anyone's phone number is not accurate, that phone numbers that we have, then it'll be kind of hard to get in touch with you. So if you see a number that you don't necessarily recognize and you're expecting a call, you should still answer it. Yeah.
Quick question, Scott. About identifying yourself. If you're talking to somebody for 30 minutes, what's the wisdom behind identifying yourself repeatedly? Is that because other people can hear you?
Yeah, because you're not just talking to that one person. I mean, think of it as a big party line.
Oh yeah.
Everybody can hear you. There's one thing that we don't have, which is privacy. So if you're going to be talking to somebody and it's going to be a private conversation, it's better to use the phone.
Mm-hmm.
Scott, I've got a question. On the reading guide we were going through, when is it permissible to transmit messages encoded to obscure their meaning? Does that also attain to encryptions? Like, is there ever a time as an amateur operator where you're able to use encryptions?
Well, I mean, if you think about it, there are lots of encryption schemes that are used, right? So long as the decryption scheme is publicly available, it's fine.
Okay.
I mean, most digital codes are in some way encrypted. I mean, if you listen to teletype or any number, of ways of sending ASCII characters or packet, they're all encrypted somehow. It's just we don't really think of them as encryption. It's a coding scheme. So you can't use a coding scheme that isn't publicly known.
Gotcha. Okay.
So, and that's why the wording is such that you're not allowed to do anything to obscure the meaning, which means that if it's something it's not, it's unable to be decrypted or unable to be decoded by the general public, you're not allowed to do it with a very few exceptions.
Got it. Thank you.
There are other services for that.
I have a bizarre question. Do you ever use geology to focus radio waves like mountain ranges or cliffs?
Yes. We have one guy who, he was actually up at somewhere around Mount Hood. And he actually aimed his antenna out at Mount Hood, which was north of him, and got into our repeater, which was south of him.
Oh, okay.
Bounced his signals off of Mount Hood.
Thanks.
Hey, Scott, it's Rob.
Uh-huh.
Hey, just a comment, just kind of for the group. I know I haven't said anything up to this point, but my boys just took the radio merit badge, and Scott was their counselor. So I've been kind of working with Scott for the last 2 to 3 months. What got us in contact with Scott was my boys actually got offered to take a totally different ham radio class online, and started realizing the difference between Scott and the other guy, that I believe Scott was a much better instructor. But one of the things that's really helping my boys get kind of caught up to get their ham license was doing the section by section instead of just doing the practice tests. We were finding that a lot of the same questions were coming up, and we weren't getting very far as many questions, because there's like 400 and some odd questions, right, Scott?
Like 430 questions.
And if you're only getting 35 on a test, so his suggestion of doing the bisection is really, really helpful. So, you know, it was a tremendous help when he said do it that way.
Thank you.
Thank you.
Thank you. That's to John or Tyler.
That was Taylor. Taylor Robin Ryden.